The stars twinkle silently, beyond the reach of time, in a universe that stretches far beyond our comprehension. Each one of those stars, from the nearest to the farthest, tells a story of light that has traveled across vast distances for billions of years, reaching us in the present moment. What we see when we look up at the night sky is merely a fraction of a reality that stretches so far, it seems infinite. We are but a tiny speck in the grand design, yet our curiosity pushes us to ask the questions that have plagued us for centuries. What is out there? What mysteries does the universe hold, waiting to be discovered? Look at the stars closely. Some of them are older than our own planet, some will outlive the Earth itself. And yet, they continue to burn brightly in the cold vacuum of space, as if they have no end. But not all stars are alike. Some are fleeting, their light a brilliant flash before they vanish. Others will endure for billions of years, quietly illuminating the vastness of the cosmos. As the light from these distant stars travels to us, it carries with it a piece of history, light from stars that were born long before the Earth itself came into being. And though we are mere observers, these stars tell us about the past, about the birth of the universe, about the very forces that have shaped our existence. We live on a tiny planet, orbiting a single star, inside a vast galaxy that is just one of billions. Our solar system, with its planets, moons, and asteroids, is only a speck in the great expanse. Yet, this tiny speck is home to us. And within this seemingly small corner of the universe, life has flourished. Humans have risen to ask questions, seek knowledge, and gaze in wonder at the mysteries of the heavens. Space is a vast, cold, and silent place, and yet, it holds secrets that make us feel both insignificant and extraordinary. We are but a fleeting moment in the grand timeline of the cosmos, but our quest to understand it is timeless. And that is the most human of all desires, to reach beyond the stars and find meaning in the vast unknown. We will venture together into this immense cosmos, exploring the stars, the galaxies, and the mysteries that lie beyond the limits of our imagination. As we travel further into the unknown, we will uncover the facts and the truths that bind us to the stars, the very same ones that have been with us since the beginning of time. Let us begin with the awe-inspiring reality of the universe's size and scale. A universe so vast, it is almost beyond the ability of our minds to comprehend. Part 1. The awe-inspiring journey. The cosmic vastness and the wonder of space. Space is not empty. It is a magnificent, vast ocean of mystery. A place so vast, it makes the Earth seem small, fragile, and fleeting. The universe stretches out before us, an endless expanse of stars, planets, and galaxies that beckon us to understand them, to uncover their secrets. It's a reminder that no matter how much we discover, we are always at the threshold of something greater, something more extraordinary than we could have ever imagined. Look up at the stars and you are looking into the past. Each star that you see is a window into history, a light that traveled millions, sometimes billions, of years to reach your eyes. The universe, in its sheer scale, holds mysteries that no human could have ever predicted. Stars are born in fiery nurseries within giant clouds of gas and dust, and from these stars, galaxies form, stretching across the cosmos in patterns that are both beautiful and unpredictable. The sheer size of the universe is something that is almost impossible to grasp. It is far beyond our everyday experience, far beyond our planet. But perhaps understanding its vastness is a place to start. The observable universe alone spans over 93 billion light-years across. In simple terms, that means it would take light, the fastest thing in the universe, 93 billion years to travel from one end to the other. And light travels at an astonishing 186,282 miles per second. We live in the Milky Way, a galaxy with around 100 billion stars, each one with the potential for planets of its own, perhaps even life. But the Milky Way is just one galaxy among the billions in the observable universe. That's not even considering the galaxies that may exist beyond what we can see. Each galaxy, a collection of billions of stars, planets, and cosmic dust, serves as a beacon in the vast expanse of space, shining its light through the darkness of time. Some stars, like our own sun, will shine for billions of years before they eventually burn out. But other stars burn bright for only a few million years, ending their lives in violent supernova explosions, releasing heavy elements into the surrounding space, which in turn will give birth to new stars and planets. These deaths of stars feed the creation of new worlds, making the cosmos a never-ending cycle of life, death, and rebirth. There is no true end to the expanse of space, only an ever-expanding frontier. Galaxies move away from us at incredible speeds, driven by the expansion of space itself, a phenomenon that was first discovered in the early 20th century. This expanding universe means that the universe is growing larger each moment, taking the stars and galaxies further from us, making the task of exploring it even more daunting. Yet, with each discovery, we grow a little closer to understanding. We've come to know that stars come in all sizes, colors, and stages of life. Some are red giants, bloated and burning through their fuel at an alarming rate. Others are blue, hot, and powerful, burning brighter than almost any other star. Some stars even collide in a fiery embrace, creating intense bursts of light that we call supernovae. In each of these events, new elements are created, many of which are necessary for life as we know it. Our own bodies, in fact, are made from elements that were formed in the cores of ancient stars. Among these stars lies something even more mysterious: black holes. Once a star has exhausted its fuel, it can collapse in on itself, creating a point in space where gravity is so strong that nothing, not even light, can escape. These invisible monsters are scattered across the universe, and their pull is so powerful that they can even bend light and warp time itself. Black holes remain one of the most fascinating and least understood objects in the cosmos, and scientists have only recently started to unlock their secrets. But not all of space is violent or chaotic. Much of it is quiet and serene. The empty stretches between stars, known as interstellar space, are surprisingly peaceful. Within these quiet areas, the few particles that exist float serenely, barely interacting with one another. And yet, these empty spaces are vital for the structure of the universe. They act as the channels through which galaxies, stars, and all matter flow. Without them, the universe would collapse into chaos. Then there is the solar system itself, a small but fascinating corner of the cosmos. Our solar system, nestled within the Milky Way, is just one of countless other solar systems. The sun, our star, is at the heart of it all, a glowing ball of energy that provides the warmth and light essential for life on Earth. Surrounding it are the planets, their moons, and other objects like asteroids and comets, each on its own journey through space. But even in our solar system, there is still much to discover. Our Earth, seemingly so big when we stand on its surface, is, in fact, tiny when compared to the size of the sun. The sun could easily hold over 1 million Earths inside of it. And Earth itself is just a speck in the solar system, which is itself just one small part of the Milky Way galaxy. To understand the enormity of space is to understand our smallness in it. And yet, it is also a reminder that this very speck is home to everything we know, everything we care about. But as vast and as mind-boggling as the universe is, it remains one of our greatest inspirations. It sparks our curiosity, fuels our imagination, and drives us to ask the questions that have been with us for centuries. How did it all begin? Where did we come from? And, perhaps the most compelling question of all, are we alone in this immense universe? The answers may be hidden in the stars, and we are only just beginning to unlock their secrets. We are at the very beginning of our understanding of the universe. Each discovery we make is a step forward in a journey that has no clear endpoint. But for now, it is enough to know that we are part of something far greater, something beyond our understanding, something that has been unfolding for billions of years. And the greatest part of it all, we are not simply observers of this vast cosmos. We are participants, our lives and actions woven into the very fabric of space and time. Let us move forward into this incredible universe, exploring the mysteries of the stars, planets, and the very forces that bind them together. With every step we take, the cosmos becomes a little less unknown, and we, in turn, become a little more connected to the magnificent story that stretches out before us. The cosmic vastness and the wonder of space. Continued. Space is not just a place. It is a living, breathing entity, constantly expanding, evolving, and changing. It's filled with wonders that go beyond the bounds of our understanding. But, despite how vast it is, the more we uncover, the more we realize that the universe has a rhythm, a pulse that transcends what we can see. Every discovery brings us closer to understanding this grand, cosmic dance. When we look at a star, we see only the light that has traveled through space to reach us. But that star, whether it's burning brightly or nearing the end of its life, is constantly in motion. It's not static. It is part of the ongoing rhythm of the universe. And as it moves, it leaves behind clues that tell the story of its life. Light traveling across vast distances is often our only way of understanding what's happening in places so far away that we can never touch them. A star's color, its size, and its temperature all tell us something about its life cycle. Some stars burn hot and fast, shining blue or white, while others glow red, their cooler temperatures giving them an ancient, tired appearance. When they burn through their fuel, some stars collapse under their own gravity, creating black holes, where even light cannot escape their grasp. The universe is alive, constantly shifting, ever-changing. The particles of the cosmos are in motion, drawn by the gravitational dance between stars, galaxies, and the forces that hold them together. The most fundamental force in space, the one that governs everything from the formation of stars to the path of planets, is gravity. It is gravity that shapes the stars, creates galaxies, and holds the planets in their orbits. This force, though invisible, dictates the motion of everything in space, bending light and time, making it one of the most powerful, yet mysterious forces we have yet to fully understand. Within this cosmic web, our solar system is just one of billions of others. Our sun, a middle-aged star, is far from unique in the grand scheme of things. It exists in a galaxy of hundreds of billions of stars, each with its own planets, moons, and mysteries. Yet, despite being just one among countless others, our solar system holds a singular importance to us. It is home. It is the place where life thrives, where humanity looks up at the stars and asks the timeless questions. Where did we come from? Are we alone? What lies beyond? The planets that surround our sun, from Mercury, the closest, to Neptune, the farthest, each tell a story of their own. Mercury, a desolate, scorched world, exists as a reminder of the harsh extremes of space. Venus, with its thick clouds of sulfuric acid, is a hellish place, where temperatures rise higher than even the surface of Mercury. Earth, our home, sits comfortably in the habitable zone, the perfect distance from the sun to sustain life. Mars, the red planet, draws our gaze with its mysterious history, a world that once may have harbored life, now barren, but still full of secrets waiting to be uncovered. And then there are the gas giants, Jupiter, Saturn, Uranus, and Neptune. These massive planets are unlike anything we can find here on Earth. They are giants of gas, surrounded by moons, rings, and mysteries. Jupiter, the largest of them all, is a stormy world, its great red spot a raging storm that has lasted for centuries. Saturn, with its spectacular rings, is one of the most beautiful sights in the solar system, a true wonder of space. Beyond our solar system, we find even more mysteries. The discovery of exoplanets, planets orbiting other stars, has opened up new realms of possibility. Thousands of these worlds have been discovered, some potentially capable of supporting life, others too hot, too cold, or too far to ever be hospitable. But in these worlds, in their orbits and in their atmospheres, we find a mirror of our own Earth, a mirror that tells us that perhaps we are not as unique as we think. The search for life beyond Earth is one of the greatest quests of our time. The discovery of extremophiles, organisms that live in the most extreme conditions on Earth, has given scientists hope that life could exist in places previously thought inhospitable. Could life exist on Mars, in the frozen moons of Jupiter and Saturn, or in the vast reaches of space itself? While we have yet to find conclusive proof, each new discovery brings us closer to the answer. Every fact we uncover, every question we answer only leads to more questions. The universe is an endless puzzle, and each piece we uncover reveals a deeper layer of mystery. The speed of light, the bending of space-time, the formation of stars, the structure of galaxies. These are just the beginning. As we learn more about the cosmos, we begin to see that everything is connected. From the smallest particles to the largest galaxies, everything in the universe is bound together by the same forces, the same laws of physics, and the same cosmic rhythms. And yet, for all its complexity, space is also remarkably quiet, peaceful. A silence that invites reflection. A silence that allows us to pause, to think, to wonder. In that stillness, we are reminded of our place in the grand scheme of things. We are part of a larger whole, one that is constantly unfolding, a journey that stretches back billions of years and will continue for billions more. In this quiet, in this stillness, we find the most profound comfort. We've barely begun to explore the mysteries of space, but with each discovery, we come closer to understanding our place in this vast, magnificent universe. For some, space is a reminder of our smallness, our fleeting existence. For others, it is a symbol of hope. A hope that one day we will unravel all the secrets of the cosmos. A hope that one day we will find the answers to the questions that have haunted humanity for centuries. And so, we continue our journey through the stars, through the galaxies, through the very fabric of space-time itself, knowing that with every step we take, we are one step closer to understanding the universe and our place within it. Space holds endless mysteries, but it also offers us a sense of peace. A peace that comes with knowing that, despite how vast the universe is, we are part of it. We are connected to the stars, to the planets, to everything in the cosmos. And that connection is a bond that transcends time and space. Teaser facts to set the mood. There are more stars in the observable universe than grains of sand on all of Earth's beaches. Yes, you heard that right, billions upon billions of stars, scattered across a vast expanse that stretches beyond our comprehension. Imagine every grain of sand on every beach on Earth, multiplied many times over, and that's just the stars we can see. The universe is filled with more stars than we could ever count. Now think about black holes, these mysterious giants. A black hole's gravitational pull is so strong, not even light can escape. Nothing, not even the fastest thing in the universe. A black hole is a cosmic vacuum, pulling everything into its abyss, where the laws of physics break down. Once something crosses the event horizon, the point of no return, it's lost forever, swallowed by the black hole's insatiable hunger. Then there's the sun, the heart of our solar system, so massive that Earth could fit inside it 1.3 million times. A single sun could hold all the planets in our solar system, and still there would be room for more. We live on a tiny planet orbiting a star that, in the grand scale of the universe, is just one of hundreds of billions in the Milky Way. Yet, without it, none of this would be possible. This is just a tiny taste of the fascinating truths that space has to offer. These facts, strange, awe-inspiring, and mind-boggling, serve as a reminder of how much there is to discover and how little we actually know. Each new discovery opens the door to even more questions, mysteries that have captivated humanity for centuries. But as vast and as mysterious as space is, it also offers us an invitation to learn, to explore, and to wonder. Every star, every galaxy, every black hole, every planet is part of a greater story, one that stretches back to the very beginning of time. And as we uncover these facts, we begin to understand not just the universe, but our place within it. These are just a few of the incredible truths about the cosmos, facts that make us pause, reflect, and marvel at the enormity of everything around us. And the journey of discovery is far from over. Every new fact brings us closer to unlocking the secrets of the universe. Yet, as we journey forward, it's clear that there will always be more to explore, more to understand, and more to wonder about. Part 2. The Boundless Universe. Vastness of space with new facts and new angles. Do a little exercise. Stand on a beach and look at the sand beneath your feet. Now visualize the stars. There are more stars in the universe than all the grains of sand on Earth. A staggering number. It's as if each grain of sand holds a star, waiting for its turn to shine in the sky. These stars are scattered across galaxies, swirling and forming clusters, bound by the powerful force of gravity. And yet, for all their numbers, they're only a small part of the vast tapestry that is the cosmos. Even though we can see only a fraction of the stars in the night sky, their light travels vast distances to reach us. Some of the stars we observe no longer exist, their light simply taking so long to reach Earth. This means that when we look up at the stars, we are not only looking at distant objects, but also peering into the past. What we see is the light that has traveled for millions, even billions, of years across the dark expanse of space. The distance between us and these stars is almost incomprehensible. For instance, Proxima Centauri, the closest star to our Sun, lies over 4 light-years away. That means the light from Proxima Centauri, traveling at 186,282 miles per second, takes over 4 years to reach us. And yet, this star is merely a neighbor in the grand scheme of the galaxy. The Milky Way, our own home galaxy, contains more than 100 billion stars, and it's just one of billions of galaxies in the observable universe. Now, let's consider the size of the universe in a different way. The observable universe is estimated to be about 93 billion light-years across. This vast distance means that we are only seeing a tiny fraction of the entire universe. And even though it is mind-boggling to think of the vastness, the universe itself may be much larger than what we see. There may be galaxies, stars, and entire regions of space far beyond our current reach, waiting to be discovered by future explorers. But what's truly fascinating is that, despite how far away these stars are, they are not stationary. They are all moving, and some at incredible speeds. The Andromeda Galaxy, for example, is on a collision course with our Milky Way galaxy. In about 4 billion years, the two galaxies will collide and merge, forming a new galaxy altogether. Yet, even this monumental event seems like a blink of an eye when placed against the timeline of the universe. Let's talk for a moment about the mysterious and awe-inspiring forces at play in the universe. Gravity is one such force. It pulls everything together, shaping stars, planets, galaxies, and even light itself. In fact, gravity is so strong that it bends the very fabric of space and time. This is the essence of Einstein's theory of general relativity. Gravity not only pulls objects towards one another, it also curves space and time around massive objects. This effect is particularly noticeable near black holes, where gravity is so intense that it warps the space around them beyond our understanding. Space itself isn't empty, either. It is filled with what is called dark matter and dark energy, two mysterious entities that together make up about 95% of the universe's total mass and energy. While we can't directly see or measure them, scientists know they must exist because of the way galaxies move and interact with each other. Dark matter doesn't emit or absorb light, making it invisible to our instruments, yet its presence is felt through its gravitational effects on the visible matter in the universe. Even more baffling is the discovery of dark energy. This is the force driving the accelerated expansion of the universe. For most of history, scientists thought that gravity would eventually slow the expansion of the universe. But in the late 20th century, it was discovered that the universe is actually expanding faster, not slower, thanks to the push of dark energy. This means that galaxies are moving away from each other at an accelerating rate, and that the universe itself will continue to grow larger and larger, stretching further into the void. In the vastness of space, everything is connected. From the smallest particles to the largest galaxies, everything follows the same fundamental laws of physics. These laws govern the motion of planets, the formation of stars, the behavior of light, and even the unfolding of time itself. Everything, from the most distant star to the smallest speck of dust, follows the same principles that allow the universe to function in its delicate balance. Consider the planets in our own solar system. While Earth is a tiny speck in the immense scale of the universe, it is a remarkable one. We are fortunate to be in what is called the Goldilocks zone, the perfect distance from the sun that allows life to thrive. Just a little closer and Earth would be too hot, a little farther and it would be too cold. the existence of life on Earth is a rare and precious thing, one that makes our planet all the more extraordinary when compared to the rest of the cosmos. As we explore further, we find other worlds, some familiar and others completely alien. Mars, for example, is often called Earth's twin. Though it is much smaller and colder, it shares many similarities with our planet, including the presence of seasons, polar ice caps, and evidence of past water. For years, scientists have been searching for signs of life on Mars, exploring its surface with rovers and orbiters, trying to answer the age-old question: was there ever life on the red planet? Beyond our solar system, the search for exoplanets, planets that orbit stars outside our sun, has yielded remarkable results. Thousands of exoplanets have been discovered, many of which reside in the so-called habitable zone of their stars. These planets, although distant, raise the exciting possibility that life could exist elsewhere in the universe. With each discovery, the possibility of finding Earth-like planets grows, and the dream of interstellar travel becomes just a little bit more real. As we continue to study space, we learn more about the cosmic forces that shape the universe. We witness the formation of stars, the death of massive supernovae, the dance of galaxies, and the eternal pull of black holes. But even more than that, we come to realize that we are not separate from space. We are part of it. Our atoms were formed in the hearts of stars, and the very air we breathe is the product of processes that began billions of years ago. And so, as we look to the stars and beyond, we are not just looking outward, we are looking inward as well. We are connected to the cosmos, woven into the fabric of space-time. And every new discovery brings us one step closer to understanding not only the universe but ourselves. Exploring the scale. Space is not just vast, it's a concept that is beyond our ability to truly fathom. It stretches beyond what we can touch or measure, and yet, it is all around us. From the very ground we stand on to the farthest reaches of the observable universe, space is everywhere, woven into the fabric of our existence. The sheer scale of the universe doesn't just lie in the distances between stars or galaxies. It lies in the size of the structures that make up the cosmos. Take a galaxy, for example. A galaxy isn't just a collection of stars. It's a complex structure of swirling arms, dust clouds, star clusters, and dark matter, all held together by gravity. Galaxies come in all shapes and sizes, from massive ellipticals that span hundreds of thousands of light-years to spirals, like the Milky Way, that curl like pinwheels of stars. Each galaxy is a vast island, floating in an ocean of other galaxies, each one incredibly far from the next. And when we look beyond the galaxies, we see something even more mind-boggling: the voids. These enormous gaps between the dense clusters of galaxies, where almost nothing seems to exist, are not empty in the strictest sense. While they may lack stars and planets, they are filled with dark matter and radiation, invisible yet ever-present. These voids stretch across unimaginable distances, sometimes billions of light-years wide, and serve as the framework for the larger structure of the universe. It's not just that the universe is huge, it's that it's full of complexity on a scale we can't quite perceive. The universe has no central point, no starting or ending place. Instead, it is an ever-expanding tapestry, continuously weaving itself into new patterns that challenge our understanding. The forces that shape this vast expanse are so powerful that they stretch the very fabric of space-time. Every galaxy, star, and planet is a part of this ongoing cosmic evolution. In our everyday lives, we are familiar with time as something linear. Seconds pass, minutes go by, and days turn into years. But in the grand scale of the universe, time behaves differently. It's not just that things take longer to happen in space. It's that the passage of time itself is influenced by the objects and forces within space. Massive objects like stars and black holes warp time, bending it around them. To those who are near them, time passes slower. This effect, called time dilation, shows us how time itself is stretched by the massive scales of the cosmos. And yet, despite the extraordinary size of space, it's easy to forget how dynamic it is. Space is constantly changing, constantly moving. Galaxies collide, stars are born and die, and cosmic radiation pulses through the emptiness, carrying with it the history of the universe. What we see as static, when viewed in our lifetimes, is in fact full of motion, with every particle and every galaxy involved in a never-ending dance. It's this movement, this transformation, that defines the very essence of space. When we look up at the night sky, what we see is only a snapshot, a brief glimpse of a universe in motion. The stars we see aren't necessarily where they once were. In fact, many of them are moving so fast that they may no longer be visible by the time their light reaches us. The idea of static objects in space is a misconception. Even the most distant stars are part of an ever-changing, ever-moving system, pulled by the forces of gravity, caught in the cosmic ballet of the universe. Now, consider how space operates on a structural level. We often think of the universe in terms of galaxies, stars, and planets, but there's something even more fundamental at play: the cosmic web. This is the large-scale structure of the universe, a vast network of galaxies, clusters, and superclusters that form intricate, thread-like structures. These massive filaments of galaxies are interconnected by vast cosmic voids, creating a web-like structure that gives the universe its large-scale shape. It's a grand design that spans billions of light-years, and yet, it's just a small part of the ever-evolving nature of space. On a cosmic scale, space doesn't just contain things, it holds the blueprint of how the universe has evolved, and how it will continue to evolve. The very laws of physics are etched into this structure, determining how galaxies form, how stars die, and how black holes devour matter. The mysteries of dark matter and dark energy, still largely unknown, play a crucial role in the universe's structure. They bind the universe together in ways we don't fully understand yet, but their presence is undeniable. Space isn't a passive environment. It's an active participant in the story of the cosmos. This scale of space, this sense of how everything is interconnected and evolving, leads us to a realization: we are not separate from the universe. We are woven into it. The atoms that make up our bodies were formed in the hearts of stars that lived and died long before Earth existed. The molecules in the air we breathe, the water that sustains life, all come from the same cosmic processes that formed the first stars and galaxies. In that sense, we are not just observers of space, we are part of it, shaped by it, and inextricably linked to it. Think about the stars. They are the building blocks of the universe, the fundamental sources of energy that fuel everything we see around us. They are born in the cold, dense clouds of gas and dust in space. These stars provide the energy that enables life, but they also shape the universe itself. When stars die, they release incredible amounts of energy, sometimes in the form of supernovae, which are some of the most powerful explosions in the universe. These explosions are so intense that they spread the heavier elements necessary for life across the universe. Without these stars and their explosive deaths, the elements that make up our bodies would not exist. Every single atom in our bodies was once part of a star. The scale of space is not just about the enormity of distance or the size of objects. It's about the profound effects that the universe has on everything within it. Time, space, matter, and energy all work together to form the universe as we know it. But as much as we understand, we are still on the very edge of discovery. Each new fact, each new discovery, pushes the boundaries of our knowledge, challenging us to think bigger, to question more, and to stretch the limits of our understanding. Visualize distances between galaxies, stars, and planets. Let's take a moment to grasp the concept of distance in space and how truly vast it is. When we think about distances on Earth, we usually measure in miles or kilometers. But space doesn't follow those rules. The distances in space are so enormous that even our familiar measures become irrelevant. We need a new scale to begin understanding how far apart things truly are. Consider the vast emptiness between stars. The distance between Earth and our closest star, the Sun, is 93 million miles. This is what we call one astronomical unit, a standard way of measuring distances within our solar system. But that's just the beginning. When we look to the stars, the distances expand dramatically. Take Proxima Centauri, for example, the closest star to our Sun. At 24 light-years away, it's almost impossible to imagine. 1 light-year is roughly 5.88 trillion miles. And even though Proxima Centauri is relatively close, it still takes over 4 years for its light to reach us. When you begin to look at the distances between galaxies, that scale increases even more. The Milky Way, our home galaxy, stretches over 100,000 light-years across. That's 100,000 years for light to travel from one edge to the other. It's hard to conceptualize, but consider this. If you could somehow travel at the speed of light, it would take you over 100,000 years to cross just the Milky Way. And that's just one galaxy in a universe full of billions of others. Let's put this in perspective. Imagine traveling to the Andromeda Galaxy, the nearest large galaxy to the Milky Way. At 2.5 million light-years away, the distance to Andromeda is so immense that it challenges our understanding of time and space. If you traveled there at the speed of light, it would take you 5 million years to reach it. The very concept of time becomes almost meaningless when distances are this long. In the scale of the universe, even the most advanced spacecraft ever built would take tens of thousands of years to reach Andromeda. To illustrate the scale of these distances, let's take a closer look at our own solar system. From Earth, let's imagine we could travel directly to Mars. At their closest, Mars and Earth are about 34 million miles apart. It sounds like a lot, but it's only a fraction of the vastness of the universe. To put that into perspective, if you were to travel at 60 miles per hour, it would take you about 23 days to reach Mars from Earth. However, the distances between planets in our solar system can vary greatly. The farther we go out, the more space opens up between objects. When you reach the outer planets, Jupiter, Saturn, Uranus, and Neptune, the distances grow exponentially. Jupiter, the largest planet in our solar system, sits about 484 million miles from the Sun. To travel from Earth to Jupiter, you would have to cross nearly 5 times the distance between Earth and the Sun. The farther we go out, the more space stretches between planets, until we reach the farthest point, Neptune. Neptune orbits the Sun at about 2.7 billion miles. These distances are mind-boggling, but even at such great distances, the solar system is just a small part of the universe. Let's zoom out further. The Milky Way galaxy is home to roughly 100 billion stars, and it stretches over 100,000 light-years. But the Milky Way isn't alone. It's part of a larger cosmic neighborhood known as the local group. The local group is a collection of about 54 galaxies, all gravitationally bound to each other. It's not just the Milky Way and Andromeda that make up this group, but a variety of smaller galaxies too, each contributing to the cosmic web. The distances between these galaxies are staggering. Andromeda, our closest large neighbor, is just 2.5 million light-years away. But other galaxies in the local group are even farther, some stretching over 10 million light-years. When you look at the universe on a larger scale, we realize that our galaxy is only a small speck in the cosmic ocean. The observable universe is 93 billion light-years across, filled with billions of galaxies, each containing billions of stars. Yet, this is only the part of the universe we can see, what we can observe. We know that the universe is far larger than what we can measure. There are regions beyond the observable universe that we will never be able to see or explore, places so distant that their light hasn't had time to reach us yet, even though the universe has existed for over 13.8 billion years. In the grand scheme of things, the distances between objects in space become a blur. The light that travels across space stretches over unimaginable distances and through vast emptiness, revealing the incredible scale of the cosmos. These distances are not just vast in terms of measurement, but in terms of the time it takes for light to travel between them. For example, if you look at a star that's 10,000 light-years away, you're seeing the light that was emitted by that star 10,000 years ago. You're seeing a moment in time that's far in the past, not the present. The sheer scale of this time and distance is hard to understand but necessary if we are to truly appreciate the scale of space. Even the light itself, which moves faster than anything else in the universe, still takes an enormous amount of time to cross these vast distances. The light from the Sun reaches Earth in about 8 minutes, but the light from Proxima Centauri, the closest star, takes over 4 years to arrive. Imagine what it means for us to observe a star that is millions of light years away. We are witnessing light that began its journey long before humans even existed. It's a humbling thought that the light from many of the stars we observe is ancient, having traveled across the universe for millions, even billions, of years before it reaches us. Despite these massive distances, space is full of potential. The gaps between stars, the space between galaxies, though incredibly vast, are not empty. They are filled with dark matter and radiation. These unseen forces stretch across the cosmos, shaping galaxies, stars, and even our own Milky Way. Dark matter, invisible to the naked eye, accounts for a significant portion of the universe's mass. Though we cannot see it directly, we can measure its effects. It's an invisible thread, binding galaxies together, influencing their movement, and playing a crucial role in the structure of the universe. To grasp these distances, we need to adjust our sense of time. It takes light over 4 years to travel to Proxima Centauri, but even at light speed, we can't imagine how long it would take to explore just our own solar system, let alone the vast expanse between galaxies. Time and distance in space aren't just numbers. They represent an unimaginable reality, one where human scale simply cannot apply. The speed at which we move, the time it takes for light to reach us, the vastness of the spaces between us and everything else. Each of these elements plays a part in revealing the true scale of the universe. The birth of stars. In the heart of dense nebulae, stars are born, like new suns, igniting the darkness and creating light where there was once nothing. These nebulae, vast clouds of gas and dust, are the cosmic cradles where new stars take form. But how does a star come to life in these dark, cold clouds? It begins with the pull of gravity. Gravity is the architect of the universe. It's a subtle yet powerful force, drawing particles of gas and dust together, slowly creating regions of higher density. Over time, these dense areas grow larger as gravity pulls in more and more matter. The process starts off slowly, but it gains momentum as the mass increases. As the gas particles collide, they generate heat. This heat builds up in the core of the nebula, causing the temperature to rise dramatically. Once the temperature reaches a critical point, the core begins to glow, signaling the birth of a new star. This early stage of star formation is chaotic, a swirling mass of gas and dust. These young stars are often surrounded by bright, colorful clouds of gas and dust, regions known as stellar nurseries. Within these nurseries, the energy from the forming star pushes the surrounding gas away, clearing space for the new star to shine. As the star continues to grow, nuclear fusion begins. It's at this moment that a star truly comes to life. Deep within the core, hydrogen atoms collide with such force that they fuse together, forming helium and releasing an enormous amount of energy in the process. This energy pushes outward, balancing the inward pull of gravity. This delicate balance between gravity and fusion is what keeps a star alive, allowing it to shine for millions, sometimes billions, of years. Stars are not born equal. Some are small and dim, destined to live quiet, long lives. These stars will burn their fuel slowly, stretching out their existence over vast periods of time. Others are much more massive and hot. These stars burn through their fuel rapidly, shining with intense light, often in brilliant blues and whites. They live fast and die young, their lives marked by explosive endings. When a star's life comes to an end, the forces within it are no longer balanced. The core may collapse under its own gravity, triggering a massive explosion, what we call a supernova. This explosion can outshine an entire galaxy for a short time, scattering elements like iron, carbon, and oxygen into the surrounding space. These elements are the building blocks of everything we know, including life on Earth. But before the end of their lives, stars often go through incredible transformations. Some stars, after exhausting their fuel, expand into red giants, swelling to many times their original size. In these later stages, they shed their outer layers into space, creating beautiful planetary nebulae. These colorful shells of gas and dust are often mistaken for the birthplaces of stars, but in fact, they are the remnants of dying stars, their final gift to the universe. Other stars, far more massive, become supernovae. These supernovae release immense energy and scatter heavier elements throughout the galaxy, which will later form new stars, planets, and perhaps even life. A supernova is the universe's way of recycling. The death of one star gives birth to the possibility of many others. The energy from these explosions also plays a key role in the formation of black holes, regions of space where gravity is so strong that not even light can escape. Yet, star formation doesn't stop at a single generation. Every new star that forms is part of a cycle that stretches across eons. When stars explode in supernovae, they scatter the very elements that make life possible. These elements spread across the galaxy, and in time, they gather to form new nebulae, new stars, and even planets. Throughout the universe, stars live and die in these endless cycles. Each generation of stars builds upon the previous one. The elements we are made of, carbon, nitrogen, oxygen, were once inside the cores of long-dead stars. We are made of stardust, the remnants of long-forgotten stellar explosions, and we carry within us the memory of those ancient cosmic events. Stars don't just create light, they create the conditions for life. Without the heat and energy from stars, our planet would not exist. Without the heavy elements forged in the hearts of stars, the Earth would be barren and lifeless. It is in the furnace of a star that the atoms that make up the world around us are formed. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was once inside a star that lived, died, and exploded. The birth of a star is a story of transformation. It starts with cold, dark clouds of gas, and ends with a blazing ball of light. In between, there's a violent and beautiful process that shapes the very fabric of the universe. The stars are the architects of the cosmos, building and shaping the galaxy with each new generation. Even as stars die, their legacy lives on. New stars are born from the ashes of the old, and the cycle continues. The universe, as vast as it is constantly creating and recreating, building itself up through these cosmic processes. And in the end, the light of a single star can travel across the universe, lighting up the darkness and revealing the incredible story of creation, destruction, and rebirth. Part 3: Black Holes, the Cosmic Mysteries. Introduction to black holes. Black holes are not empty space. They are regions of space where gravity is so strong that not even light can escape their grasp. Imagine a place where the very fabric of space-time is distorted beyond recognition, pulling everything in, compressing matter into a point so dense, it's beyond our ability to fully comprehend. These cosmic giants are among the most mysterious and fascinating objects in the universe, and understanding them is key to unlocking the deeper secrets of space itself. A black hole is defined by one simple but profound property: its event horizon. The event horizon is the boundary around a black hole beyond which nothing can return. Once anything, whether it's light, matter, or even information, crosses this line, it's trapped forever. Even the fastest thing in the universe, light, cannot escape. This is why black holes are black. They don't emit light. Instead, they absorb everything, leaving us only to study their effects on the surrounding space. What makes black holes so intriguing is their power to alter the very structure of space-time. Space and time are not independent of one another. They are intertwined, forming what's known as space-time. And black holes warp space-time in the most extreme way imaginable. Around a black hole, time slows down as you get closer to the event horizon. For an observer far away, it would seem as though time for anything near a black hole slows to a crawl. But from the perspective of something falling in, time moves just as it always does, normal and uninterrupted, until the moment of no return. The concept of a black hole is rooted in Einstein's general theory of relativity, which describes how gravity works on a cosmic scale. According to this theory, mass and energy warp the space-time around them, and when something massive like a star collapses under its own gravity, it can create a black hole. While the mathematics behind black holes is extremely complex, their effects can be observed across vast distances in space. One of the most striking features of a black hole is its ability to influence everything around it. Despite being invisible, Black holes can be detected by their effect on nearby stars and gas clouds. When material falls into a black hole, it can form a swirling disk of hot gas around it, known as an accretion disk. This disk, which can reach millions of degrees, emits powerful radiation that can be detected by telescopes. In fact, these glowing disks of gas are often the brightest objects in the universe, far outshining the stars in their galaxy. Black holes come in different sizes, ranging from stellar mass black holes, which form when massive stars collapse, to supermassive black holes, which sit at the centers of most large galaxies. These supermassive black holes can be billions of times the mass of our Sun, and their gravitational influence extends across entire galaxies. Some of the most energetic phenomena in the universe, like quasars, are powered by the immense energy produced by material falling into supermassive black holes. Despite their intense gravitational pull, black holes don't go around sucking everything in their vicinity. Their influence is strong, but only within a limited range. Objects that are far enough away from a black hole, like stars in the galaxy, will continue their orbits without ever falling in. In fact, the Sun, despite being much smaller than a supermassive black hole, exerts far more influence over the solar system because of its proximity. Black holes only affect their surroundings when objects venture too close, crossing the event horizon and becoming irretrievably lost. One of the most perplexing things about black holes is that they don't only absorb matter, they also seem to affect information. The so-called information paradox remains one of the biggest unsolved mysteries in physics. According to the laws of quantum mechanics, information cannot be destroyed. But when something falls into a black hole, it seems to be lost forever. Scientists are still working to understand how information behaves in these extreme conditions. Some believe that information is preserved on the event horizon, while others propose that it might be encoded in the radiation emitted by the black hole. What makes black holes even more fascinating is that we may never truly understand all of their mysteries. The conditions near a black hole, where gravity is so intense that it warps space-time, are so extreme that even our most advanced theories of physics break down. It's in these regions, where the known laws of physics no longer apply, that we might find new physics. And the search for answers continues to push the boundaries of our understanding of space, time, and the universe itself. In a sense, black holes are gateways to new realms of science, offering clues to the nature of the universe and the very structure of reality. Their gravitational pull and mysterious behavior challenge our notions of what is possible, forcing us to rethink the way we view space, time, and matter. As our understanding of black holes deepens, we may one day uncover the secrets hidden within them, revealing not just how the universe works, but why it works the way it does. Black holes, in their very nature, embody the extremes of the universe. They are where the ordinary rules of nature break down, creating a cosmic puzzle that continues to intrigue scientists and lay people alike. The search to understand them is ongoing, with new discoveries and breakthroughs happening regularly. And with each new piece of the puzzle, we get one step closer to unraveling the profound mysteries that these dark giants hold. The formation of black holes. Black holes are born when massive stars collapse under their own gravity, leaving behind a point of no return. But how does this incredible transformation take place? To understand the formation of a black hole, we need to first explore the life cycle of a star, especially the most massive ones. Every star begins its life by converting hydrogen into helium through nuclear fusion in its core. This process releases a tremendous amount of energy, balancing the inward pull of gravity that tries to collapse the star. For most stars, this balance between gravity and fusion lasts for billions of years. But for massive stars, the story unfolds differently as they near the end of their lives. As a massive star runs out of fuel, fusion in its core slows down, and the balance begins to shift. With no energy to oppose the force of gravity, the core starts to collapse inward, and the outer layers of the star expand and cool, forming a red giant. This is a critical point in the star's life. If the star is massive enough, the collapse continues. The core becomes increasingly dense and hot, and at a certain point, it forms what is known as a singularity, a point of infinite density where the laws of physics as we know them break down. At this stage, The core has become so dense that it can no longer hold itself up against the crushing force of gravity. If the star's mass exceeds a critical threshold, typically around 3 times the mass of the Sun, the collapse becomes unstoppable. The core continues to compress, and eventually, it reaches a state where not even light can escape the gravitational pull. This marks the birth of a black hole. But before it reaches this final point, the dying star often experiences a spectacular explosion, a supernova. This cataclysmic event is one of the most powerful explosions in the universe, releasing an enormous amount of energy and scattering heavy elements, like iron, oxygen, and carbon, into the surrounding space. These elements will later go on to form new stars, planets, and even life, but the core of the star remains behind, collapsing into a black hole. A black hole's defining feature is its event horizon, the boundary beyond which nothing, no matter, no light, can escape. Once the core has collapsed past this point, the black hole is fully formed. The event horizon marks the edge of the black hole, and it's this line that separates the known universe from the unknown. Anything that crosses the event horizon is lost forever, swallowed into the blackness. What happens inside the event horizon, beyond the point of no return, is still one of the greatest mysteries in physics. But the process isn't limited to the collapse of individual stars. Some black holes, known as supermassive black holes, are believed to form at the centers of galaxies. These giants can have masses millions, even billions, of times that of our Sun. The exact process behind their formation is still uncertain, but it is thought that they might form from the merger of smaller black holes, or from the accumulation of gas and dust over time, gradually growing larger and larger. Supermassive black holes can hold entire galaxies within their gravitational grasp, shaping the formation and evolution of the galaxies around them. Interestingly, while black holes are often viewed as destructive forces, they also play a vital role in the cosmos. Their intense gravity pulls in material from their surroundings, forming accretion disks that can emit powerful radiation. This radiation can illuminate vast regions of space, allowing us to study black holes and their surroundings from billions of light years away. Black holes help to regulate the growth of galaxies, control star formation, and even influence the movement of entire galaxies. They are integral to the cosmic cycle of birth and death in the universe. Although black holes can appear to be voids of space, they are anything but empty. They are active, dynamic entities, constantly pulling in matter and bending the fabric of space-time itself. The more we learn about black holes, the more we realize that they are not just cosmic oddities. They are crucial players in the evolution of galaxies and the universe as a whole. The process of star death and black hole formation is a reminder of the cyclical nature of the cosmos. Stars are born, live out their lives and die, and in their deaths, they leave behind the possibility for new worlds and new stars to form. In the case of a black hole, that death becomes a gateway into the unknown, a place where our understanding of physics is stretched to its limits, where the boundaries of space and time blur into something entirely new. As we continue to study these incredible objects, we unlock more secrets about the universe itself. The formation of black holes is not just about the collapse of a star. It is about the transformation of matter and energy, the very fabric of space-time being altered in ways we are only beginning to understand. The existence of black holes challenges our perceptions of reality and forces us to ask questions that go to the heart of the universe's most fundamental mysteries. From the collapse of a massive star to the creation of a supermassive black hole at the center of a galaxy, the formation of black holes is a cosmic event that represents the very nature of change, of rebirth and destruction. And with each new discovery, we come closer to unlocking the secrets hidden within these enigmatic objects, discovering how they influence everything around them, and perhaps even how they fit into the larger story of the universe. Visualizing black holes. Black holes are among the most extraordinary phenomena in the universe, yet their nature is elusive, hidden behind the veil of extreme gravity. Time, space, and even light bend and warp in ways that defy our understanding, especially near a black hole's event horizon. Time slows down and becomes distorted near the event horizon, where the gravity is most intense. Anything that crosses this point is lost forever. The event horizon represents the boundary of a black hole, an invisible line that, once crossed, marks the point of no return. For an outside observer, it would appear as though an object falling into a black hole slows down and never quite reaches this boundary, stretching out as if time itself is stretching. But for the object itself, everything continues as normal, without any awareness of the event horizon's presence. It's an uncanny, paradoxical scenario, one that leaves scientists grappling with the consequences of this distorted reality. This effect, known as time dilation, happens because of the intense warping of spacetime near a black hole. Space and time are intimately connected in Einstein's theory of relativity. When an object falls toward a black hole, the gravitational pull distorts both space and time, so that time moves slower the closer you get to the event horizon. This means that, for someone far away, a clock near the black hole would appear to tick more slowly. As you approach the event horizon, the slowdown becomes more pronounced, and it seems as though time itself is stretching out infinitely. But from the perspective of the object falling in, time moves normally. It's a contradiction that challenges our basic understanding of how time works. Now, consider the immense gravity that shapes a black hole. This gravitational force is so strong that not even light can escape it. Light, the fastest thing in the universe, cannot outrun a black hole's pull. When light gets close enough, it's trapped by the black hole, unable to escape. This is why black holes appear completely dark. However, the area just outside the event horizon is often surrounded by an accretion disk, a swirling mass of gas, dust, and debris. As these materials spiral inward, they heat up to extreme temperatures, emitting X-rays and other radiation. This glowing disk is one of the only ways we can detect black holes, despite their invisibility. A black hole doesn't simply consume everything in its path. Objects that are far enough away from the event horizon can continue their normal motions, orbiting the black hole just as planets orbit stars. For instance, stars orbiting a supermassive black hole in the center of a galaxy can maintain stable orbits for millions or billions of years without being consumed. It's only when objects venture too close, crossing that crucial event horizon, that they are swallowed into the black hole's grasp. But what happens to matter once it crosses the event horizon? This is a question that has intrigued scientists for decades. According to general relativity, once something crosses into the black hole, it is crushed into a singularity, a point of infinite density where the laws of physics as we know them break down. This singularity lies at the very center of the black hole at its core. Everything that falls into a black hole is compressed into this infinitesimally small point, where gravity is so intense that the normal rules of spacetime cease to function. Despite the dramatic nature of a black hole's interior, the exact details of what happens inside are still largely unknown. The singularity is a place where the very concept of space and time lose all meaning, a region where even the most advanced theories of physics break down. We have no way of observing the interior of a black hole, and this fundamental mystery leaves us at the edge of understanding. What lies beyond the event horizon, where all things are crushed into a point of infinite density, is beyond our reach, perhaps forever. But black holes do not remain static. They can grow and evolve by consuming matter from their surroundings. This material often forms an accretion disk, a spinning disk of gas and dust that spirals inward, heating up as it gets closer to the black hole. This disk is one of the most energetic objects in the universe, emitting intense radiation as it gets closer to the event horizon. In fact, some black holes, particularly supermassive black holes, are so massive and powerful that they can launch jets of particles at nearly the speed of light from their poles, creating enormous structures of energy that stretch for millions of light years. These jets are some of the most awe-inspiring phenomena in the universe, showcasing the immense power that black holes can exert. Supermassive black holes, found at the centers of galaxies, can have masses billions of times that of the Sun. These behemoths govern the galaxies they inhabit, with their gravity influencing the orbits of stars and the shape of the galaxy itself. In many ways, supermassive black holes shape the destiny of their galaxies. Some scientists believe that the formation of these massive objects may have been central to the development of the galaxies they inhabit, playing a crucial role in regulating star formation and the growth of cosmic structures. But while black holes themselves remain shrouded in mystery, they are also the key to unlocking some of the deepest questions about the universe. The study of black holes challenges our understanding of gravity, space, time, and matter. Every new discovery about black holes provides new insights into the fabric of the cosmos and the forces that govern it. As we continue to observe these enigmatic giants, we come closer to understanding how the universe works at its most fundamental level, and perhaps even unlocking the secrets of space-time itself. In a sense, black holes are the ultimate cosmic puzzle. They embody the extremes of space and time, bending the very fabric of the universe into shapes we cannot fully comprehend. They represent both the beginning and the end of everything, where stars are born and die, and where the fundamental laws of physics break down. As we peer into their depths, we are reminded of how much more there is to discover, of how much of the universe remains hidden, waiting for us to unravel its mysteries. Part 4: Our Earth and its tiny place in space. Size comparison. Earth is but a speck in the vastness of space. Could fit inside the Sunday, January 3rd million times. And yet, it is our home, the cradle of life, a small, fragile sphere suspended in the cosmic ocean. Despite its size, Earth is unique. It is the only known place in the universe where life, as we understand it, thrives. This tiny planet, orbiting an ordinary star, holds the entirety of our existence. And though it seems large when we stand on its surface, the scale of the universe quickly puts that into perspective. When we look at Earth from space, it appears as a delicate blue ball, floating within a sea of darkness. Its beauty is breathtaking, but it is also fragile, a rarity in the vastness of the cosmos. The Earth's atmosphere, our protective shield, is incredibly thin compared to the planet's size. If you could stretch the Earth out into a perfect sphere, the atmosphere would be no thicker than the skin of an apple. It's hard to grasp how thin and vulnerable our protective layer is, especially when we consider the size of the universe and the infinite space that surrounds us. Our planet's size is dwarfed by the stars, which range in size from tiny red dwarfs to massive blue giants. If you were to place Earth inside the Sun, it would take over 1.3 million Earths to fill the Sun's vast volume. The Sun, a medium-sized star, is by no means the largest star in the universe, yet its enormous size is more than enough to make our planet seem insignificant by comparison. The Sun makes up over 99% of the mass of our entire solar system, with its gravity holding the planets, moons, asteroids, and comets in their orbits. It is a gentle giant, but a giant nonetheless, radiating energy that sustains life on Earth and shapes the dynamics of our solar system. The size of stars varies greatly. Our Sun, while large in comparison to Earth, is considered an average-sized star in the grand scheme of the universe. Some stars are much larger. Take the star Uy Scuti, for example. It is so large that, if placed at the center of our solar system, its outer edge would extend past the orbit of Jupiter. Its volume is over 5,000 times that of the Sun. Such massive stars are a reminder of how small our Sun truly is in the context of the universe. Even though the Sun provides us with warmth and light, it is just one of billions of stars scattered across the universe. However, not all stars are giants. The smallest stars, known as red dwarfs, are much smaller than the Sun, yet they are the most common type of star in the universe. These tiny stars can be as much as 50 times less massive than the Sun and are barely visible to the naked eye. Despite their size, they burn for much longer than larger stars, sometimes living for trillions of years. This means that while Earth might seem like a speck, the stars around it vary greatly in size, each with its own story to tell. When you step back and consider the size of the universe itself, the vastness becomes even more overwhelming. The Milky Way galaxy, which contains our solar system, is over 100,000 light-years across. That means if you could travel at the speed of light, it would take you 100,000 years to travel from one side of the galaxy to the other. And this is just one galaxy among billions. Our galaxy is part of a larger structure called the local group, a cluster of more than 50 galaxies. Even that is just a tiny part of the enormous universe. The observable universe stretches over 93 billion light-years across, a vast expanse that contains countless stars, planets, and galaxies. To comprehend this size is almost impossible for the human mind. And yet, here we are, a tiny speck of life, floating within this immense cosmic ocean. The scale of the universe is not just vast, it is almost beyond human comprehension. The distances between objects in space are so large that even light, which travels at a speed of 186,282 miles per second, takes years, sometimes millions or billions of years, to travel from one point to another. To give you a sense of scale, the nearest star to Earth, Proxima Centauri, is over 4 light-years away. That means light takes over 4 years to travel from that star to Earth. But Proxima Centauri is only the closest star outside our solar system. Many stars are much farther away, stretching the fabric of the universe beyond what we can easily grasp. The observable universe is just a small portion of the total universe. The distances we measure are limited by the speed of light and the age of the universe itself. Because light takes time to travel, we are essentially looking into the past when we observe distant stars and galaxies. The farther away an object is, the older the light is that we see, making the universe not just vast, but also ancient. When we observe galaxies billions of light-years away, we are seeing them as they were billions of years ago, long before our Sun and Earth even existed. In the grand scheme of the cosmos, Earth is a mere dot, an insignificant blip in a universe that is both ancient and vast. And yet, despite its small size, Earth is the only place we know of that supports life. The fact that life exists on a planet this small is one of the greatest wonders of the universe. It serves as a reminder that while we are a tiny part of the cosmos, our existence, our consciousness, and our ability to contemplate the stars is something extraordinary. In the face of such overwhelming vastness, Earth remains our precious home, unique and fragile in the infinity of space. The scale of the solar system. Our solar system is a vast space, yet it's only a small part of our galaxy, which is itself just one among billions in the universe. The scale of the solar system is difficult to grasp because, in the grand context of the universe, it is small, remarkably small. But even within that scale, the distances between the planets and their relationship to one another create an awe-inspiring sense of vastness. At the center of our solar system is the Sun. It accounts for 99.86% of the entire mass of the solar system. To put this into perspective, if the Sun were the size of a basketball, Earth would be the size of a small pea, and it would be orbiting about 26 feet away. The Sun's gravitational pull is what holds the entire solar system together, with its powerful gravity keeping the planets, asteroids, and comets in their orbits. Every single object within our solar system is influenced by the Sun's immense gravitational force. But even though the Sun dominates the solar system, it is only a single star, and compared to the rest of the universe, it's considered average. There are stars far larger, far more massive, and far older than our Sun, scattered across the Milky Way and beyond. And within the solar system itself, the planets vary dramatically in size and distance from the Sun. Let's start with the inner planets: Mercury, Venus, Earth, and Mars. These are the rocky planets made up of solid surfaces. Mercury, the closest planet to the Sun, is small and hot, with temperatures that can reach over 800 degrees Fahrenheit during the day. Venus, often called Earth's twin because of its similar size, has a thick, toxic atmosphere and surface temperatures that are even hotter than Mercury's. Earth, our home, sits comfortably in what is known as the habitable zone, a region around the Sun where conditions are just right for liquid water to exist. Mars, the red planet, is a world full of mysteries, with evidence that liquid water once flowed on its surface but now exists only as ice beneath the dusty surface. Beyond Mars, the scale starts to shift dramatically. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are known as gas giants, and they are enormous compared to the inner planets. Jupiter, the largest planet in our solar system, could fit over 1,300 Earths inside it. Saturn, with its magnificent rings, is nearly as massive but slightly less dense. Uranus and Neptune, though smaller than Jupiter and Saturn, are still giant planets, made mostly of gas and ice. These planets are far from the Sun, which means they receive much less heat and light, making them cold, inhospitable worlds. The distances between these planets are staggering. For example, Earth and Mars are separated by an average of about 140 million miles. But to travel to Neptune, the farthest planet from the Sun, you would have to travel nearly 3 billion miles. The vastness of the space between planets is almost beyond what we can easily comprehend. If you could travel at the speed of light, it would take over 4 hours to travel from the Sun to Neptune. And that's just one solar system nestled within our galaxy. Now, take a step back and think about the scale of the Milky Way galaxy, the home of our solar system. The Milky Way spans about 100,000 light-years across, a distance so vast that it's hard to even imagine. If you could travel at the speed of light, it would take you 100,000 years to travel from one side of the galaxy to the other. And even though our solar system is located in one of the galaxy's spiral arms, the entire Milky Way contains about 100 billion stars, many of which have planets orbiting around them. Our Sun is just one of those stars, in a universe that is filled with many others. Our solar system itself is not static. It's constantly in motion. The Sun and its planets orbit the center of the Milky Way at a speed of about 514,000 miles per hour. And yet, even at this incredible speed, it takes the Sun about 225 million years to complete one orbit around the galaxy's center. This period is known as the galactic year, and it's a staggering length of time compared to the span of a human lifetime. As the solar system moves through the galaxy, it travels through regions filled with cosmic dust, gas clouds, and other stars, making our solar system's journey both dynamic and ongoing. But the solar system is not isolated in space. It is part of a much larger cosmic structure known as the Local Group, a collection of over 50 galaxies, including the Milky Way and the Andromeda Galaxy, which is on a collision course with our galaxy. And beyond the Local Group are billions of other galaxies, each with its own stars, planets, and potential for life. As vast as our solar system is, it is just one of billions of systems scattered across the universe. The scale of our solar system might seem overwhelming, but it's only a tiny part of a much larger cosmic structure. The further we move outward, the more we realize that the solar system, and even our galaxy, is just a small piece of an even more immense and complex universe. The distances between the stars and galaxies are so vast that, even traveling at the speed of light, it would take us millions of years to explore just a fraction of it. In the end, the size of our solar system is humbling. We live on a planet that is part of a system of planets, all orbiting an ordinary star. Yet, it is this small, fragile planet that holds all of humanity's hopes, dreams, and history. The vastness of the universe reminds us of how small we are in the grand scheme of things, but it also reminds us of how precious our existence is. The wonder of Earth. Earth, delicate and precious, is suspended in a cosmic dance, orbiting its star in perfect harmony. It is the only known planet that harbors life, a remarkable and rare occurrence in the vastness of the universe. This small blue dot, orbiting a medium-sized star, floats in the infinite expanse of space, perfectly positioned to allow life to thrive. What makes Earth unique is the delicate balance of conditions that sustain life, factors that, in their combination, create the perfect environment for all the diversity of life forms we see today. The Earth's distance from the Sun is crucial. It exists within the Goldilocks zone, an area neither too hot nor too cold, where water can exist in liquid form. Water, the foundation of life as we know it, covers about 71% of Earth's surface. Oceans, rivers, lakes, and glaciers are not just beautiful features of our planet. They are essential to the stability of our climate, the cycling of nutrients, and the sustaining of ecosystems. Without liquid water, Earth would be a barren wasteland, its surface scorched by the sun, incapable of supporting life. The atmosphere of Earth is another vital aspect of its uniqueness. It is made up of a mixture of gases, primarily nitrogen and oxygen, which provide the breathable air necessary for life. But what makes it so special is its composition, which acts as a shield, protecting life on Earth from the harsh radiation of the sun and the cold void of space. It also plays a crucial role in regulating the planet's temperature, maintaining a delicate balance between warmth and cold. This thin layer of air, only a few dozen miles deep, is what allows us to exist in this otherwise inhospitable universe. Earth's magnetic field is another factor that contributes to its habitability. This magnetic field, generated by the movement of molten iron in the planet's core, acts as a protective barrier against the solar wind, a stream of charged particles emitted by the sun. Without this magnetic shield, the solar wind would strip away the atmosphere, exposing the planet to deadly radiation and making it impossible for life to survive. The field also helps to create the beautiful auroras, visible in polar regions, as charged particles from the sun collide with Earth's atmosphere. But the most remarkable aspect of Earth is the abundance and diversity of life that it supports. Life on Earth is not a random occurrence. It is the result of billions of years of evolution, shaped by the unique conditions of the planet. From the deepest ocean trenches to the highest mountain peaks, from the coldest polar regions to the hottest deserts, Earth hosts a staggering variety of ecosystems and species. This diversity is a testament to the adaptability of life and the intricate relationships between all living things and their environment. Earth's ability to support life is not just a matter of the right conditions. It is also due to the delicate balance of systems that regulate everything from the planet's climate to the cycling of nutrients. The carbon and water cycles, the nitrogen cycle, and the complex interactions between living organisms and their environments keep Earth in a state of dynamic equilibrium. When one of these systems is disrupted, it can affect the entire planet, which is why maintaining this balance is so important for the survival of life. The presence of life on Earth also plays a role in shaping the planet itself. Plants produce oxygen, essential for the respiration of animals, while animals produce carbon dioxide, which plants need for photosynthesis. The cycling of carbon through Earth's atmosphere, oceans, and landmasses regulates the planet's climate, preventing it from becoming too hot or too cold. This interconnectedness between life and the planet's systems is a defining characteristic of Earth. Throughout Earth's history, it has experienced many changes, from the cooling of its surface to the rise of continents and the shifting of tectonic plates. Yet, despite these changes, the planet has remained a stable environment for life. This stability is no accident. It is the result of complex feedback mechanisms that regulate temperature, carbon levels, and the planet's geology. Earth's ability to maintain these conditions, even in the face of major disruptions, is a remarkable feature that sets it apart from any known planet. However, Earth's environment is fragile. Human activity has begun to alter the delicate balance that has allowed life to thrive. Climate change, deforestation, pollution, and the depletion of natural resources are just some of the challenges that we face today. These changes are happening at an unprecedented rate, and the consequences could be far-reaching, affecting everything from weather patterns to the biodiversity of ecosystems. It is a reminder that while Earth is incredibly resilient, its ability to support life depends on the careful stewardship of its resources. Yet, despite these challenges, Earth remains a place of beauty and wonder. The planet's landscapes, its forests, deserts, mountains, and oceans are not just physical features. They are the products of millions of years of geological and biological processes. The patterns of clouds in the sky, the changing colors of the seasons, the way light reflects off the surface of the water. All these are reminders of the dynamic, ever-changing nature of our planet. Even in the darkest depths of space, Earth stands as a beacon of life. It is the only place we know where life exists, and it is a treasure beyond measure. The Earth's uniqueness in the universe is a profound mystery, one that has inspired countless generations to look up at the stars and ask questions about our place in the cosmos. It is a reminder that despite the vastness of space and the countless other worlds out there, Earth is where we belong. It is our home, and it is up to us to protect it, so that future generations can continue to experience the wonders of the world we live in. Part 5: Early Space Exploration. The first journey into space. In 1947, before humans embarked on their cosmic journey, tiny fruit flies were the first to venture beyond Earth's atmosphere, traveling to study how space would affect living organisms. These small, seemingly insignificant creatures became the pioneers in humanity's quest to explore the stars. They were chosen for a very practical reason. Their simple biological structure made them ideal test subjects for the early stages of space exploration. Fruit flies, with their short lifespans and rapid reproduction, were perfect for researchers looking to understand the effects of space travel on living organisms. Scientists knew that traveling into space would expose creatures to radiation and the vacuum of space, all of which could have unknown effects on the body. By sending these tiny creatures into space, they could gather crucial data before sending humans. The mission was carried out by the United States, with the fruit flies being launched aboard a V-2 rocket in the early hours of February 20, 1947. The rocket, a product of wartime technology, was the perfect vehicle to carry these first space travelers. Though the flight was short, lasting just a few minutes, it marked a monumental step in the history of space exploration. These little insects traveled more than 70 miles into the upper reaches of the atmosphere, reaching altitudes where the effects of weightlessness and radiation could be measured. While the flight lasted only minutes, the data collected from the fruit flies helped scientists begin to understand the challenges of space travel. The flies were exposed to zero gravity and cosmic radiation, and their survival would show whether life could endure the harsh conditions of space. When the rocket landed, the flies were recovered, and scientists were thrilled to find that they had survived the flight, despite the many unknowns. This achievement, though small in its immediate scope, paved the way for future, more sophisticated missions. It was a small step for science, but it would eventually lead to sending humans into space, a feat that would inspire generations of astronauts, engineers, and explorers. The journey of those first fruit flies was part of a larger global effort to push the boundaries of what was possible, and it signaled the beginning of a new age in human history. After the success of the fruit flies, further tests were conducted with other organisms, including monkeys and mice, as the space agencies continued to gather data on the effects of space travel on living bodies. In 1957, just a decade later, the Soviet Union launched Sputnik 1, the first artificial satellite, and began the space race. This event would catapult the world into a new era of space exploration and set the stage for human spaceflight. Though the fruit flies were the first living creatures in space, their journey was just the beginning. These early missions, although brief, opened the door to more complex experiments and, ultimately, the human exploration of space. The work done with these tiny pioneers, fruit flies, provided the foundation for everything that would follow, from the first human spaceflight by Yuri Gagarin in 1961 to the moon landings and the space stations orbiting Earth today. In the early days of space exploration, the focus was not on grand missions or reaching other planets, but on learning how space travel would affect life. The fruit flies were the first to bear the weight of this new frontier, proving that life, even in its smallest form, could endure the extreme conditions of space. They were the first to venture beyond Earth's atmosphere, and though their journey was short, it was one of the most significant milestones in the history of human exploration. The bravery of these small creatures, sent into the unknown, helped lay the groundwork for the brave men and women who would follow. In many ways, the legacy of those first space travelers lives on today. In every space mission, every astronaut, and every step humanity takes in its quest to explore the vastness of the cosmos. From fruit flies to humans, the journey into space has been a story of trial, discovery, and perseverance, and it all began with those first tiny pioneers. The impact of the first human space travel. In 1961, Yuri Gagarin became the first human to travel into space, orbiting Earth and forever changing our understanding of the universe. The space race had begun. Until that moment, the idea of sending a human beyond the confines of Earth was the stuff of science fiction. But Gagarin's mission made it a reality, and with that single leap into the unknown, humanity had crossed a threshold that would shape the future of exploration, technology, and science. Gagarin's spacecraft, Vostok 1, was a small, cramped capsule that took him on a single orbit around the Earth. The entire flight lasted just 108 minutes, but those minutes were filled with groundbreaking moments. As Gagarin made his way around the planet, he became not only the first human to witness Earth from space, but also the first to experience weightlessness, the vast expanse of space, and the thrill of traveling faster than anyone ever had before. The impact of Gagarin's flight was immeasurable. It wasn't just a technological achievement. It was a symbol of what humanity could accomplish. In an era defined by the Cold War, Gagarin's flight became a powerful moment of national pride for the Soviet Union and a source of inspiration for people around the world. It was a statement that the impossible was now possible, that the barriers of space were no longer out of reach, and that the future of space exploration had arrived. More than just a demonstration of human ingenuity, Gagarin's journey changed our perspective on Earth itself. From space, the planet appeared small and fragile, suspended in the darkness of the cosmos. It was a realization that Earth, with all its life, its complexity, and its beauty, was just a tiny speck in the vast universe. A tiny speck worth protecting and cherishing. Yuri Gagarin's flight marked the beginning of the space race, a fierce competition between the United States and the Soviet Union to dominate space exploration. This rivalry would fuel incredible advancements in technology, leading to the first American manned space flights, the successful Apollo moon landings, and the eventual establishment of international space stations. While Gagarin's flight was a triumph for the Soviet Union, it was also a moment of profound significance for humanity as a whole. It showed us that space wasn't just a place for distant, unmanned probes or the subject of theoretical discussions. It was a frontier we could conquer. It was a physical realm that we could explore, with the possibility of sending humans to worlds beyond our own. After Gagarin's flight, space exploration seemed to hold limitless potential. It set the stage for the Apollo program, which would eventually put humans on the moon. It also laid the groundwork for the development of modern space agencies and international collaborations in space research. Gagarin's mission didn't just spark a race between nations. It sparked a global movement to explore the stars. But it wasn't just about the political implications of space exploration. The human spirit was forever changed by Gagarin's journey. The idea that a human being could leave Earth, float in the silence of space, and return to tell the story was both a triumph of human achievement and a testament to our curiosity and desire to push the boundaries of what is possible. The legacy of Gagarin's flight is still felt today. Every astronaut who has followed in his footsteps, from the first spacewalks to the construction of the International Space Station, owes something to that pioneering moment. The world may have seemed smaller after Gagarin's flight, but the possibilities became infinitely larger. With the knowledge that human beings could survive in space, the door was open to a future where space was no longer a dream, but a tangible frontier. Yet, even after all these years, we have only just begun to scratch the surface of what space exploration has to offer. What we know about the universe, the cosmos, and the possibility of life beyond Earth has expanded exponentially since Gagarin's historic journey. But the truth is, there is still so much we don't understand. What other wonders, challenges, and discoveries await us in the uncharted expanse of space? Only time will tell, but the journey began on that fateful day in 1961, when Yuri Gagarin became the first human to venture into the cosmos, forever changing the way we view our place in the universe. The Apollo moon landings. In 1969, Neil Armstrong and Buzz Aldrin became the first humans to set foot on the moon, marking a new chapter in human history. Their journey was the culmination of years of scientific progress, technological innovation, and a fierce competition between two superpowers, the United States and the Soviet Union. The Apollo 11 mission wasn't just about reaching the moon. It was about proving that humanity could achieve the impossible. This was the moment when dreams became reality, and the cosmos no longer seemed so distant. The Apollo program, initiated by NASA, was a response to the intense space race with the Soviet Union, which had already achieved remarkable milestones, including sending the first man-made satellite, Sputnik, into orbit and putting the first human, Yuri Gagarin, into space. The United States, determined to demonstrate its own technological might, set its sights on the moon. The challenge was immense, but it was one that would forever change the course of history. On July 20th, 1969, Neil Armstrong, the mission commander, and Buzz Aldrin, the lunar module pilot, made their way down from the Eagle, the lunar module, to the surface of the moon. As Armstrong set foot on the dusty surface, he famously declared, "That's one small step for a man, one giant leap for mankind." These words echoed across the world, symbolizing the collective achievement of all who had contributed to the Apollo mission. Armstrong's first step onto the moon wasn't just a triumph for him. It was a triumph for all of humanity. The idea that human beings could travel to another celestial body, land, and return to Earth was no longer a distant dream, but a tangible reality. The moon's surface was stark and silent, untouched by life as we know it. Yet, Armstrong and Aldrin were not alone. Their spacecraft, the Command Module Columbia, was piloted by Michael Collins, who remained in lunar orbit while Armstrong and Aldrin explored the surface. While Armstrong and Aldrin were walking on the moon, Collins circled above, keeping the Command Module steady and safe, ready to bring them back to Earth. The trio worked in perfect coordination, each man playing a crucial role in the success of the mission. While the moon may appear desolate and barren, the impact of the Apollo mission was anything but. The astronauts collected rock samples, took photographs, and deployed scientific instruments to help scientists better understand the moon's geology, composition, and potential for future exploration. Their work laid the groundwork for future lunar missions and opened the door for mankind to explore beyond Earth's orbit. The moon became our first stepping stone into the cosmos, a world that was once distant and foreign now within reach. Yet, the moon landing was not just about exploration. It was about what it represented: a triumph of human ingenuity, perseverance, and unity. It was the result of years of hard work, overcoming setbacks, and overcoming doubts. The mission brought people together across nations, as millions around the world watched in awe as humans walked on the moon. It was a symbol of what could be achieved when people from all walks of life came together with a common purpose. The Apollo 11 mission was followed by 5 other successful lunar landings, each contributing new knowledge about the moon and space. However, Apollo 11 remains the most iconic, as it marked the first time humanity had set foot on another world. The mission showed the world that space exploration was no longer a theoretical pursuit. It was real, it was possible, and it was only the beginning. Even now, decades after the first moon landing, the Apollo missions continue to inspire new generations of scientists, engineers, and explorers. The legacy of those brave astronauts lives on, not just in the technology they developed, but in the spirit of exploration they ignited in the hearts of people everywhere. It's a reminder that humanity's quest to understand the universe is far from over, and that the moon is only the first step in the journey. To this day, the Apollo 11 mission remains one of humanity's greatest achievements. It proves that with determination, collaboration, and the relentless pursuit of knowledge, we can achieve the extraordinary. As we look toward the future of space exploration, whether it's returning to the moon, sending humans to Mars, or exploring the far reaches of the universe, we carry with us the lessons of Apollo 11. The journey is far from finished. If anything, it's just the beginning. Chronology of notable astronauts. From the early days of space exploration to today, astronauts have pushed the boundaries of human achievement, each leaving a lasting impact on science, technology, and our understanding of the cosmos. Let's take a look at some of the most significant figures who have shaped humanity's journey into space. On April 12, 1961, Yuri Gagarin, a Soviet cosmonaut, made history as the first human to journey into space aboard Vostok 1. His flight, which lasted 108 minutes, marked a monumental achievement in the space race and cemented his place as a global symbol of progress. As Gagarin orbited the Earth, his successful mission demonstrated not only the technical capabilities of the Soviet space program, but also humanity's potential to reach the stars. Less than a month later, on May 5, 1961, Alan Shepard became the first American to travel into space. Shepard's suborbital flight aboard the Freedom 7 was brief, lasting just over 15 minutes, but it served as a catalyst for the United States' efforts in space exploration, highlighting the competition that was unfolding between the two superpowers. On February 20, 1962, John Glenn became the first American to orbit the Earth, completing 3 orbits aboard Friendship 7. This achievement was pivotal not just for the U.S. space program, but also for the psychological impact it had on both the American public and the world. Glenn's successful mission was a much-needed boost for the American space effort, coming just after the Soviet Union had placed the first human in orbit. Yuri Gagarin's achievement was followed by a significant milestone in 1963, when Valentina Tereshkova became the first woman to travel into space aboard Vostok 6. Her flight not only shattered the gender barrier in space exploration but also emphasized that space was an arena for all humans to explore, regardless of gender or nationality. On March 18, 1965, Alexei Leonov made history as the first human to perform a spacewalk during the Voskhod 2 mission. His 12-minute extravehicular activity, EVA, marked the beginning of a new phase in human space exploration, as spacewalks would become an essential part of future missions, including those to the moon and beyond. Meanwhile, in the United States, on June 3, 1965, Ed White followed Leonov's footsteps by becoming the first American to perform a spacewalk during the Gemini 4 mission. His 23-minute EVA demonstrated the possibility of working in space and opened the door for future space missions that required astronauts to leave their spacecraft. On December 21, 1968, the Apollo 8 mission, which included Frank Borman, James Lovell, and William Anders, became the first crewed mission to orbit the moon. This achievement set the stage for the historic Apollo 11 landing, as the team's successful journey around the moon proved that humans could travel to and orbit another celestial body. On July 20, 1969, Neil Armstrong and Buzz Aldrin made history as the first humans to walk on the moon during the Apollo 11 mission. Armstrong's iconic words, "That's one small step for a man, one giant leap for mankind," encapsulated the enormity of the achievement. The successful landing on the moon wasn't just a technological feat. It represented the triumph of human determination and ingenuity. On April 11, 1970, Apollo 13 became a dramatic chapter in space exploration. When an oxygen tank exploded in the spacecraft, astronauts James Lovell, Fred Hayes, and Jack Swigert were forced to abort their mission to the moon. Their incredible teamwork and the cooperation of NASA's ground control saved their lives, demonstrating the importance of problem-solving and human resilience in the face of disaster. On January 31, 1971, Apollo 14 astronauts Alan Shepard and Edgar Mitchell became the fifth and sixth humans to walk on the moon. Shepard, famously known as the first American in space, piloted the lunar module to the surface, and together with Mitchell, they conducted experiments and collected samples that contributed greatly to lunar science. On December 11, 1972, Apollo 17 astronauts Eugene Cernan and Harrison Schmitt became the last humans to set foot on the moon. This marked the end of the Apollo lunar exploration program. Cernan's final words as he left the moon were poignant. "We leave as we came, and, God willing, we shall return, with peace and hope for all mankind." Fast forward to 1983, when Sally Ride became the first American woman in space aboard the Space Shuttle Challenger on mission STS-7. Her groundbreaking flight opened new doors for women in space exploration, and her achievements continue to inspire young girls and women around the world to pursue careers in science and engineering. In 1984, Rakesh Sharma became the first Indian citizen to travel to space aboard the Soviet spacecraft Soyuz T-11. His flight highlighted the importance of international cooperation in space exploration, and his famous line, "Ser Jahan Se Eka," better than the entire world, became etched in Indian history. Guyon Bluford became the first African-American astronaut in space during mission STS-8 aboard the Space Shuttle Challenger in 1983. His achievement was a major milestone in diversifying the ranks of the astronaut corps and in breaking down racial barriers in the field of space exploration. Jean-Luc Crétin, in 1982, became the first French astronaut in space aboard the Soviet spacecraft Soyuz T-6. This marked a significant milestone in international space collaboration, underscoring the importance of space as a platform for global cooperation rather than competition. One of the most significant figures in space history is Mae Jemison, the first African-American woman in space. She made history in 1992 aboard the Space Shuttle Endeavour during mission STS-47. Her mission symbolized the importance of diversity in space exploration and paved the way for future astronauts of diverse backgrounds. The progression of space exploration continues to this day, with astronauts from various countries contributing to the International Space Station and planning missions to the Moon, Mars, and beyond. From the very first flight of Yuri Gagarin to the missions of the International Space Station, every astronaut's journey has contributed to expanding our understanding of space and the human spirit's capability to explore the unknown. Spaceflight records. Spaceflight is a realm where human endurance, ingenuity, and courage are tested to their limits. Over the decades, astronauts have achieved remarkable feats, setting records that showcase the extraordinary capabilities of the human spirit. Valery Polyakov holds the record for the longest single spaceflight by any human. He spent 437 days aboard the Mir space station from January 1994 to March 1995. This mission was part of a study to understand the effects of long-term space travel on the human body. Following closely is Oleg Kononenko, who has accumulated over 1,110 days in space across 5 missions. His extensive experience has provided invaluable data on human adaptation to extended spaceflight. Among American astronauts, Frank Rubio set the record for the longest single spaceflight, spending 371 days aboard the International Space Station. His mission was extended due to a delay in the return vehicle, Hyli. Christina Koch holds the record for the longest single spaceflight by a woman, spending 328 days in space. Her mission was part of NASA's efforts to study the effects of long-term spaceflight on the female body. On the International Space Station, the record for the longest continuous occupation belongs to the international partnership that has maintained a human presence in space since October 31, 2000. This ongoing collaboration underscores the importance of international cooperation in space exploration. Spacewalks, or extravehicular activities, EVAs, are critical for maintaining spacecraft and conducting experiments. The record for the most spacewalks is held by Anatoly Solovyev, who completed 16 EVAs totaling over 82 hours. Peggy Whitson, another record holder, has spent more than 60 hours outside spacecraft during her 10 EVAs, the most by any female astronaut. Sunita Williams has also made significant contributions, with 9 EVAs totaling over 62 hours, further advancing our understanding of human capabilities in space. These records are not just numbers. They represent the dedication, resilience, and pioneering spirit of astronauts who have ventured into the unknown. Each mission, each record, brings us closer to understanding how we can live and work in space for extended periods, paving the way for future exploration beyond our planet. Part 6. The speed of light and time. The concept of light speed, 186,282 miles per second. Light travels faster than anything else in the universe, moving at a speed of 186,282 miles per second, making our universe seem a little smaller in comparison. This remarkable speed allows light to cross vast distances almost instantly. When we observe stars, galaxies, or even distant planets, we are witnessing light that has traveled for millions or billions of years to reach our eyes, a reminder of just how far the universe extends beyond what we can perceive. At 186,282 miles per second, light is the ultimate speed limit of the cosmos. No object or signal can travel faster than this. In fact, this speed is so fast that it challenges our very understanding of time and distance. If you could travel at the speed of light, you would be able to circle the Earth 7.5 times in just 1 second. It's difficult to truly grasp the scale of this speed, but it's the foundation for how we understand space, time, and the very fabric of the universe. Light speed is not just a theoretical concept, it has real-world implications. For example, when we look at the moon, the light we see from it left the surface over a second ago. When we gaze upon the sun, we are seeing light that left the sun about 8 minutes ago. And when we observe stars in our galaxy, we're often looking back in time, because the light reaching us could have traveled for hundreds, thousands, or even millions of years before it arrives. But light speed isn't just about how fast light travels. It also plays a critical role in the theory of relativity, formulated by Albert Einstein. According to Einstein, the speed of light is constant, no matter how fast you are moving. This leads to fascinating and counterintuitive phenomena. For instance, as you approach the speed of light, time itself slows down for you relative to someone who is stationary. This is called time dilation, a phenomenon that has been confirmed by numerous experiments and is essential for understanding the effects of high-speed travel in space. Light speed also helps explain the vast distances between celestial objects. For instance, when we measure the distance to a star, we often do so in terms of light years. 1 light year is the distance that light travels in 1 year, roughly 5.88 trillion miles. The nearest star to Earth, Proxima Centauri, is about 4.24 light-years away. That means the light we see from that star today actually left it over 4 years ago. This concept of light years gives us a sense of how immense the distances are in our universe. While light speed might seem like an abstract concept, it is fundamental to our ability to explore and understand space. For instance, without light, we would not be able to observe the cosmos at all. Telescopes depend on light to gather information about distant objects. The patterns, colors, and intensity of light we receive from distant stars and galaxies provide clues about their composition, temperature, age, and even their motion. By studying this light, scientists can determine the movement of galaxies, detect exoplanets, and even observe the expansion of the universe itself. Yet, despite its speed, light takes time to travel even short distances in the vastness of space. For example, when we look at the nearest galaxy to the Milky Way, Andromeda, we are seeing it as it was over 2.5 million years ago. That's because the light from Andromeda has been traveling to us for that long, which means we are looking at a snapshot of a galaxy that existed long before our ancestors even walked the Earth. Understanding light speed also opens up the possibility of future space exploration. While we cannot currently travel at the speed of light, scientists are constantly exploring ways to increase the speed at which we can travel through space. Concepts such as warp drives or the theoretical use of wormholes suggest that one day, we might be able to travel vast distances across the galaxy in a matter of hours or days, instead of years or centuries. Light speed is also central to our modern technologies. Satellites rely on the speed of light to send signals to Earth from space, allowing for everything from GPS navigation to global communications. Fiber optic cables, which carry internet data, use light to transmit information at incredible speeds, connecting people around the world almost instantaneously. But for all its importance, light speed also reminds us of the limitations of our current technology and the vastness of the universe. No matter how advanced we become, the limitations of the speed of light will always influence how we explore space. Even if we could someday send a spacecraft to another star, the journey would take many years. Our current methods of propulsion simply cannot match the speed of light. Yet, the pursuit of this understanding continues, driving us to explore new possibilities and challenging the boundaries of what we can achieve. Every time we look up at the stars, we are gazing into the past, receiving the light that has traveled across the vast distances of space to reach us. Light speed serves as a bridge between the present and the distant past, offering a glimpse into the history of the universe. It's a reminder that, even in the vastness of space, light is a constant companion, guiding our exploration and expanding our understanding of the cosmos. Time and space. Time bends and stretches in the presence of massive objects. The stronger the gravity, the slower time moves. This fascinating relationship between time and space was first described by Albert Einstein in his theory of relativity. The idea that gravity can warp time might seem strange at first, but it's one of the cornerstones of modern physics and has been confirmed through countless experiments and observations. Einstein's theory of general relativity tells us that massive objects, like planets, stars, and black holes, actually curve the fabric of space and time around them. This curvature affects how time passes, and the closer you are to a massive object, the more time is stretched. This phenomenon is called gravitational time dilation, and it means that time doesn't flow uniformly everywhere in the universe. Take, for example, the Earth's gravity. It's strong enough to keep us anchored to the surface, but it's not strong enough to have a significant impact on time. However, if you were to travel closer to a black hole, where gravity is incredibly strong, time would slow down dramatically for you relative to someone far away. If you spent just a few minutes near the event horizon of a black hole, an observer far away would see you experience hours or even days in just those minutes. This stretching of time has profound implications. For astronauts aboard the International Space Station, time actually moves just a little bit slower than it does on Earth due to the weaker gravity they experience while orbiting the planet. This is a result of the effects of relativity, even at the relatively small scale of Earth's orbit. The difference is minuscule, on the order of milliseconds, but it's a real, measurable effect that has been confirmed with atomic clocks. The most extreme example of this effect occurs near black holes, where gravity is so intense that time nearly stops altogether. At the event horizon, the point of no return around a black hole, time slows to a crawl. If you were to watch someone fall into a black hole, you would see them freeze in place as they approach the event horizon. In their own frame of reference, however, they would continue to experience time normally, while everything around them would seem to happen in fast forward. Another mind-bending result of Einstein's theory is the concept of spacetime. According to general relativity, time and space are interconnected in a four-dimensional fabric. This means that time and space are not separate, but part of the same structure. When massive objects like stars or planets warp space, they also warp time. This blending of time and space is what we refer to as spacetime. This theory has profound implications for our understanding of the universe. It changes the way we view everything from the motion of planets to the path of light. For instance, light, which travels at a constant speed, can be bent by gravity, a phenomenon known as gravitational lensing. This bending occurs because massive objects like galaxies or black holes can curve spacetime, causing light from distant stars or galaxies to follow a curved path. This effect allows us to see distant objects in space that would otherwise be hidden behind other objects, expanding our view of the universe. One of the most famous confirmations of Einstein's theory came in 1919, when astronomers observed that the light from distant stars was bent as it passed near the sun during a solar eclipse. This experiment proved that space was indeed curved by gravity, just as Einstein had predicted. It was one of the first pieces of direct evidence supporting his theory of general relativity, and it forever changed how we understood the nature of time and space. Even more fascinating is the idea that time and space are not absolute but are relative to the observer. This concept, known as time dilation, becomes especially important when considering space travel. If we could travel close to the speed of light, time would slow down for us relative to people on Earth. This means that astronauts traveling at relativistic speeds could experience only a few years of travel, while decades or even centuries could pass for those left behind. In theory, this could allow humans to travel vast distances across the universe, but it comes with the immense challenge of achieving speeds close to the speed of light. However, even without the extreme conditions near black holes or the need for relativistic space travel, time and space continue to influence our daily lives. For instance, GPS satellites orbiting the Earth experience both special and general relativity. Because they are moving quickly and farther from Earth's gravity, the clocks on these satellites tick slightly faster than those on the ground. If these relativistic effects weren't accounted for, GPS systems would be inaccurate by miles in just one day. Understanding the relationship between time and space opens up incredible possibilities for the future. It encourages us to rethink the very nature of time and how we measure it. It also offers a new perspective on the vastness of the universe and our place within it. The idea that time itself can stretch and bend challenges our fundamental notions of reality and underscores the mysterious, complex nature of the cosmos. Time and space, once thought to be independent and unchanging, are now understood as part of a dynamic, flexible system that responds to the forces acting upon it. From the simplest atomic clocks to the most powerful black holes, the connection between time and space governs the behavior of everything in the universe, influencing the orbits of planets, the paths of light, and even the flow of time itself. Part 7: Mysteries of Other Planets. The gas giants and their moons. Jupiter and its moon along with its vast planetary system. Jupiter, the largest planet in our solar system, is a giant, a massive swirling ball of gas and clouds. It's not just big in size, it's big in its influence. It's a gas giant composed mainly of hydrogen and helium, and it's so massive that it could fit over 1,300 Earths inside it. Jupiter's immense size and powerful gravity make it a dominant force in our solar system, playing a crucial role in shaping the orbits of nearby bodies and influencing the dynamics of the solar system itself. Jupiter's atmosphere is a spectacle of swirling clouds, driven by powerful winds and storms. The Great Red Spot, a storm large enough to engulf Earth, has been raging for at least 400 years, possibly much longer. The clouds above the planet are composed of ammonia, methane, and water vapor, creating an environment that's both mysterious and hostile to life as we know it. Despite the inhospitable conditions, scientists study Jupiter to understand more about gas giants and planetary atmospheres. But Jupiter isn't just fascinating for its composition and storms. Its moon system is equally extraordinary. Jupiter has at least 79 known moons, with 4 of them standing out for their size and importance. These are Io, Europa, Ganymede, and Callisto, collectively known as the Galilean moons, discovered by Galileo Galilei in 1610. These moons are not just satellites. They are worlds unto themselves, each with its own unique features and mysteries. Io, the innermost of the Galilean moons, is the most volcanically active body in the solar system. Its surface is constantly reshaped by hundreds of volcanoes that erupt with molten sulfur, creating a landscape that looks more like a fiery hellscape than a moon. The intense volcanic activity is caused by tidal heating, a result of the gravitational pull from both Jupiter and its neighboring moons, which causes the interior of Io to flex and generate immense heat. Europa, the second moon from Jupiter, is perhaps the most intriguing of all. Beneath its icy surface, scientists believe there is a vast, global ocean of liquid water. This ocean is kept warm by tidal forces exerted by Jupiter's gravity, creating the potential for a habitable environment beneath the ice. The surface of Europa is covered with cracks and ridges, suggesting that the ice sheet is shifting and moving, which only adds to the mystery of what might lie beneath. Ganymede, the largest moon in the solar system, is even larger than the planet Mercury. Ganymede stands out not only for its size, but for its own magnetic field, the only one found on a moon. Its surface is a patchwork of 2 types of terrain, one darker and older, full of craters, and the other lighter, marked by ridges and grooves. This contrast suggests that Ganymede has experienced geological activity, perhaps even an internal ocean, similar to Europa's. Callisto, the farthest of the 4 Galilean moons, is an ancient world, covered in craters, and with a surface that appears to have remained largely unchanged for billions of years. Callisto's lack of significant geological activity may make it an important target for future exploration. Its surface is mostly made of ice and rock, and its deep craters provide clues about the solar system's history. These 4 moons alone represent an incredible diversity of geological processes and environments, from fiery volcanoes to frozen oceans, from ancient craters to potentially habitable oceans beneath the surface. Jupiter's moons offer some of the most exciting prospects for scientific exploration in the entire solar system. Jupiter's influence doesn't stop with its moons. Its massive gravity acts as a cosmic vacuum cleaner, attracting comets, asteroids, and other space debris that might otherwise threaten Earth. Jupiter's position as the largest planet in the solar system allows it to capture or deflect objects that could potentially collide with Earth, providing a kind of shield for the inner planets. Some scientists even suggest that Jupiter's gravity has helped shape the structure of the asteroid belt, preventing these objects from coalescing into another planet. Jupiter's immense gravity also plays a crucial role in shaping the orbits of other planets, especially the outer planets in the solar system. It has long been suspected that Jupiter's gravity might have even played a role in the formation of the solar system itself, helping to scatter material and influence the paths of other planetary bodies during the early days of the solar system. Over the years, several spacecraft have visited Jupiter and its moons, each mission providing new and incredible insights into this giant world. NASA's Juno spacecraft, which entered orbit around Jupiter in 2016, is studying the planet's atmosphere, magnetic field, and overall structure. Meanwhile, the Galileo spacecraft, which orbited Jupiter from 1995 to 2003, helped to uncover many of the secrets of the Galilean moons, providing vital data on Europa's potential for life. Future missions to Jupiter are set to explore even deeper mysteries. The European Space Agency's Jupiter Icy Moons Explorer, JUICE mission, scheduled for launch in the coming years, will study the moons Europa, Ganymede, and Callisto in detail, searching for signs of habitability and further investigating the possibilities of subsurface oceans. As we continue to explore Jupiter and its moons, we come closer to answering some of the most profound questions about our solar system. How did the planets form? Could there be life beyond Earth? What secrets does the gas giant hold beneath its swirling clouds? Jupiter, with its vast size, incredible moons, and strong gravitational influence, stands as a gateway to the mysteries of the outer solar system. Jupiter's planetary system is a living laboratory, a place where science fiction meets reality, where humanity's understanding of space, time, and life itself is constantly evolving. It's a world that invites us to ask, not just how planets and moons form, but what role they play in the grand, cosmic story of the universe. Saturn and its moon along with its vast planetary system. Saturn, the sixth planet from the Sun, is one of the most iconic and fascinating worlds in our solar system. With its brilliant golden hue and stunning rings, it stands out as a celestial jewel. Saturn's size and composition, like Jupiter, mark it as a gas giant, primarily made up of hydrogen and helium. But Saturn is unique not just for its size, but for the intricate system of rings that surround it. Rings made of billions of icy particles, each one orbiting the planet in an elegant, cosmic ballet. The most distinguishing feature of Saturn, of course, is its magnificent ring system. These rings, while beautiful to observe, are incredibly complex. They consist of ice and rock particles, ranging in size from tiny dust grains to large chunks of ice. Despite their vast size, stretching out more than 140,000 kilometers from Saturn's surface, the rings are incredibly thin, often no more than 1 kilometer thick. It is this contrast, the vastness in size and the delicacy of the rings, that makes them one of the most mysterious and captivating features of the planet. But Saturn's wonders don't end with its rings. Its moons are a story all on there, with more likely to be discovered in the future. These moons range from small, icy bodies to large, complex worlds, each with its own unique features and mysteries waiting to be explored. The largest of Saturn's moons is Titan, a world that has fascinated scientists ever since it was first discovered. Titan is unique among the moons of the solar system, not only because it is larger than the planet Mercury, but because it has a thick atmosphere. In fact, Titan's atmosphere is mostly nitrogen, much like Earth's, but it also contains methane and other hydrocarbons. This has led scientists to compare Titan's atmosphere to that of Earth billions of years ago, before life began. The thick clouds of methane and nitrogen give Titan a yellowish hue and hide its surface, making it an intriguing, yet mysterious, world. On Titan's surface, lakes and rivers of liquid methane and ethane exist, creating a landscape that is strikingly similar to Earth's water-based features, but on a much colder, more hostile world. Despite the lack of liquid water, the presence of liquid hydrocarbons on Titan makes it the only other known body in the solar system with stable liquids on its surface. This raises the possibility that Titan could hold clues to the processes that might lead to life elsewhere in the universe. Further investigations into Titan's atmosphere and surface have revealed the presence of complex organic molecules, essential building blocks for life. Although the temperatures on Titan are incredibly low, around -290 degrees Fahrenheit, -179 degrees Celsius, the discovery of these complex molecules has made Titan a key target in the search for life beyond Earth. The Cassini spacecraft, which explored Saturn and its moons for over 13 years, provided invaluable data about Titan, including a close flyby of the moon in 2005 that revealed vast seas of liquid methane and ice, along with signs of potential cryovolcanism, volcanic activity involving the eruption of icy material rather than molten rock. Another fascinating moon of Saturn is Enceladus. While much smaller than Titan, Enceladus has captured the imagination of scientists due to the discovery of water vapor geysers erupting from its icy surface. These plumes of water vapor contain organic molecules, which makes Enceladus one of the most promising places to search for life. Beneath Enceladus' icy shell, there is strong evidence of a subsurface ocean, warmed by tidal forces from Saturn's gravity. This ocean could harbor the necessary ingredients for life to exist, and future missions to this moon may provide answers to one of the most profound questions in science. Could life exist elsewhere in our solar system? Then there is Mimas, the Death Star moon, so named because its appearance resembles the iconic battle station from Star Wars. Mimas has a massive crater known as Herschel, which is 1/3 the size of the moon itself. This impact crater suggests that Mimas has been subjected to significant collisions in its history. Despite its battered appearance, Mimas is thought to have a relatively smooth surface, indicating that it may have experienced some form of internal heating in the past. Saturn's moon Rhea, on the other hand, is less dramatic but still intriguing. This icy moon has a very low density, which suggests it is made primarily of water ice with a small core of rock. Rhea is known to have a thin, tenuous atmosphere made up of oxygen and carbon dioxide, but its weak gravitational field means that this atmosphere is not stable and quickly dissipates into space. Beyond Saturn's main moons, there are smaller, less well-known moons that are equally fascinating. Moons like Iapetus, with its two-tone coloration, one hemisphere bright and white, the other dark and heavily cratered, continue to puzzle scientists. Theories about Iapetus' strange appearance range from the possibility of ancient volcanic activity to the effects of solar radiation on its surface. Saturn's moons are not just diverse in their physical characteristics, but also in their interactions with the planet and its rings. Many of Saturn's moons are in orbital resonance with one another, meaning that their orbits are linked by gravity. For example, the moons Mimas, Enceladus, and Tethys are locked in a gravitational dance, where their movements influence each other, creating complex tidal forces that drive geologic activity on the moons, like the eruptions on Enceladus. Saturn's planetary system also offers insights into the formation and evolution of the solar system. The rings, moons, and the planet itself are thought to have formed about 4.5 billion years ago from the same swirling disk of gas and dust that created the Sun and the rest of the planets. However, some scientists believe that Saturn's rings might be much younger, possibly only a few 100 million years old, and may have formed after the planet's birth from the collision of icy moons or comets. Saturn's immense gravity and its array of moons and rings continue to make it a focus of scientific study. The Cassini spacecraft, which studied Saturn and its moons for over 13 years, provided an unprecedented look at the planet's atmosphere, its magnetic field, and its ring system. It also discovered many of the features we've discussed: oceans beneath icy moons, active volcanoes on Io-like bodies, and the potential for life in places like Titan and Enceladus. Future missions to Saturn's moons, such as the planned Dragonfly mission to Titan, are expected to build on the findings from Cassini, delving even deeper into the mysteries of this complex system. These missions may provide the first evidence of life beyond Earth, or reveal new and unexpected phenomena that challenge our understanding of the universe. Saturn's planetary system is a vast and intricate world in itself, teeming with mysteries, beauty, and scientific importance. From its massive rings to its diverse moons, Saturn is not just a planetary giant. It is a window into the formation of the solar system, a potential harbor for life, and an essential step in our ongoing exploration of space. Uranus and its moon, along with its vast planetary system. Uranus, the seventh planet from the Sun, is a world that stands out in many ways. Unlike the other planets in our solar system, Uranus rotates on its side, tilted at an extreme angle of about 98 degrees to its orbit. This means that, rather than spinning like most planets with its poles pointed toward the Sun, Uranus rolls around the Sun, almost like a bowling ball. This unique feature has made Uranus one of the most intriguing and mysterious planets to study. Uranus is a gas giant, composed mainly of hydrogen, helium, and ices like water, ammonia, and methane. Its icy blue color comes from methane in the atmosphere, which absorbs red light and reflects blue light back into space. The planet is cold, with temperatures in its upper atmosphere plunging to -224 degrees Celsius, making it one of the coldest places in the solar system. Despite its extreme tilt, Uranus experiences seasons, much like Earth. However, because of its tilted rotation, its seasons are far more extreme. A single season on Uranus lasts about 21 years. For a full year on the planet, the Sun shines directly on one pole for 21 years, and then it shines on the opposite pole for the next 21 years. This strange seasonal pattern is caused by its unusual axial tilt, making Uranus one of the most unusual planets to study in terms of its seasonal changes. Uranus is surrounded by a complex system of rings and moons, While it's not as well known for its rings as Saturn, Uranus has 13 rings that are faint, narrow, and made up of dark particles. These rings are much less pronounced and harder to observe than Saturn's, but they are nonetheless a crucial part of Uranus' planetary system. The rings are believed to be relatively young, possibly the result of a collision or the breakup of a moon in the past. Uranus moons are similarly fascinating, with 27 known moons orbiting the planet. These moons are all named after characters from the works of William Shakespeare and Alexander Pope. The 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are among the most intriguing objects in the outer solar system. Miranda, the innermost of the 5 largest moons, is a world of extremes. Its surface is a patchwork of bizarre geological features, including large cliffs, valleys, and canyons. Some scientists believe that Miranda may have been shattered and reassembled in the past, which could explain the strange and varied surface features. The moon has a very low density, suggesting it is mostly made of water ice and rock, and it is thought to have experienced intense tidal forces in the past that caused the surface to crack and shift. Ariel, slightly larger than Miranda, has a much more youthful surface, filled with canyons, valleys, and smooth plains. Unlike Miranda, Ariel does not show signs of being shattered and reassembled. Instead, its surface appears to have undergone some form of resurfacing in the past, possibly due to tectonic activity or icy volcanism. The moon's bright, icy surface reflects much of the sunlight that hits it, making it one of the brightest objects in the Uranian system. Umbriel, on the other hand, is much darker and more heavily cratered than its neighboring moons. Its surface is marked by deep craters, suggesting that it has remained relatively unchanged for billions of years. Umbriel has a much lower albedo than the other moons, meaning it absorbs more sunlight and is not as reflective. Its dark surface might indicate that it has a larger proportion of organic compounds or carbon-rich materials. Titania, the largest of Uranus moons, is a world of contrasts. Its surface is covered in a mix of ancient impact craters, valleys, and ice-covered terrain. Titania is thought to have once had some form of internal heating, possibly from tidal forces or radioactivity, which allowed it to undergo some degree of geological activity. The largest feature on Titania's surface is the immense canyon system that stretches for thousands of kilometers, one of the largest in the solar system. Oberon, the second largest moon of Uranus, is similarly icy and rocky. Its surface is heavily cratered, suggesting that it has remained largely inactive for most of its history. Like many of Uranus' moons, Oberon is thought to be made up of a mixture of water ice and rock. It also has some large impact basins, which are believed to have been created by collisions with other objects in the past. The moons of Uranus are unique not just for their physical characteristics, but for their interactions with the planet itself. Unlike the moons of Jupiter and Saturn, which are heavily influenced by tidal forces due to their proximity to their planets, Uranus moons are more distant, and their interactions with the planet's gravity are much weaker. However, Uranus moons still experience tidal heating, which is most noticeable on Miranda, where extreme surface features suggest past geological activity driven by these forces. Uranus' planetary system also offers valuable clues about the formation of the solar system. Scientists believe that Uranus and Neptune, the 2 ice giants, formed further out from the Sun than the gas giants Jupiter and Saturn. This positioning could explain their composition, which is more icy and less dominated by hydrogen and helium than the gas giants. The study of Uranus moons provides insight into how these icy bodies formed and evolved over time, and what role they played in the early history of the solar system. Uranus' strange tilt, extreme seasons, and distant moons make it one of the most unique planets in our solar system. While the planet itself is difficult to observe from Earth due to its distance and faint visibility, recent missions like the Voyager 2 flyby in 1986 have provided valuable data about the planet and its moons. The information gathered by Voyager 2 continues to influence our understanding of ice giants and their role in the broader context of planetary formation. Despite being one of the least explored planets in the solar system, Uranus offers a treasure trove of information waiting to be uncovered. Scientists are eager to send a dedicated mission to explore Uranus more closely, to study its atmosphere, moons, and rings in greater detail. Such a mission could provide answers to many of the fundamental questions about planetary formation, evolution, and the potential for life beyond Earth. Uranus and its moons are far more than distant objects in the sky. They are key pieces of the cosmic puzzle. As we continue to explore these frozen, distant worlds, we move closer to understanding not just the nature of the outer planets, but the broader processes that shape the entire solar system. Uranus, with its tilted rotation and unique planetary system, serves as a reminder of the wonders yet to be explored in the far reaches of space. Neptune and its moons, along with its vast planetary system. Neptune, the eighth and farthest planet from the Sun, is a world of mystery, darkness, and incredible winds. As a gas giant, Neptune shares many characteristics with its neighbor Uranus, but it stands out due to its vibrant blue color, which comes from the methane in its atmosphere. Its deep blue hue, enhanced by the planet's extreme distance from the Sun, captures the imagination of scientists and skywatchers alike. Neptune's striking appearance, however, is only a small part of its story. Unlike the other planets in the solar system, Neptune's atmosphere is incredibly dynamic. It's marked by the fastest winds recorded anywhere in the solar system, winds that reach speeds of over 1,500 miles per hour, 2,400 kilometers per hour. These ferocious winds stir up massive storms, one of the most famous being the Great Dark Spot. This storm, similar to Jupiter's Great Red Spot, is a massive storm system that churns through Neptune's atmosphere, shifting and evolving in ways that continue to baffle scientists. Neptune is also notable for its size and mass. Though similar in composition to Uranus, Neptune is about 17 times more massive, which allows it to retain a thicker atmosphere. Beneath its atmosphere, Neptune's interior is made up of a mixture of rock, water, and ice, surrounded by a thick gaseous layer. Its interior is still a subject of ongoing research, with scientists attempting to understand the complex processes that power its immense storm systems and extreme temperatures. Neptune's magnetic field is another fascinating aspect of the planet. Unlike Earth's magnetic field, which is relatively straightforward and aligned with the planet's rotational axis, Neptune's magnetic field is tilted and offset from its center. This unusual configuration raises intriguing questions about the planet's internal structure and the forces that generate its magnetic field. Understanding Neptune's magnetism will provide vital insights into the behavior of other distant planets and their ability to sustain such intense magnetic forces. One of the most important aspects of Neptune's planetary system is its moon system. Neptune has 14 known moons, each with its own peculiarities. The largest and most famous of these moons is Triton, a moon that stands out for several reasons. First, Triton is unique in the solar system because it has a retrograde orbit, meaning it orbits Neptune in the opposite direction to the planet's rotation. This unusual orbit suggests that Triton was likely captured by Neptune's gravity, rather than having formed in orbit around the planet. Triton is also geologically active, with signs of cryovolcanism, volcanic activity involving the eruption of icy materials rather than molten rock. Triton's surface is covered in frozen nitrogen, with a terrain marked by ridges and cracks. This frozen surface is evidence of past geological activity, indicating that Triton may have once had a subsurface ocean. The discovery of geysers on Triton, spewing nitrogen gas into space, is a significant clue about the moon's internal activity. These geysers provide further evidence that Triton may still have some form of internal heat, possibly from tidal forces exerted by Neptune's gravity as it orbits the planet. Another intriguing moon of Neptune is Proteus, which is the second largest moon in the system. Unlike Triton, Proteus has an irregular shape and a heavily cratered surface, suggesting it has experienced significant impacts throughout its history. Its dark surface, made up of water, ice, and rock, reflects very little sunlight, making it one of the darker moons in the solar system. Proteus is thought to be a captured object, and its uneven shape further supports this theory. Despina, Galatea, Larissa, and Naiad are additional moons that make up Neptune's extensive and complex moon system. These moons are relatively small, irregularly shaped, and heavily influenced by Neptune's gravitational pull. Their orbits and interactions with Neptune's rings provide valuable information about the dynamics of small moons and their role in shaping planetary systems. One of the most fascinating features of Neptune's moons is their relationship with its ring system. Neptune has 5 known rings, each made up of dark particles that are difficult to see from Earth without powerful telescopes. The rings, while faint, are likely relatively young and may have formed from debris created by the destruction of a moon or from material captured by Neptune's gravity. The interaction between Neptune's rings and moons is an area of ongoing research, offering insights into the complex gravitational dynamics of moons, rings, and their evolution. One of the most mysterious aspects of Neptune's moon system is the possibility of hidden oceans beneath the icy surfaces of its moons. Triton, for example, may harbor a subsurface ocean beneath its frozen surface, and some scientists believe that other moons like Proteus and Galatea may also have similar features. These hidden oceans, if they exist, could hold the potential for life, making Neptune's moon system a prime target for future exploration. Despite Neptune's immense distance from the Sun, about 30 times farther than Earth, its moon system remains an important area of scientific study. The moons of Neptune are thought to have formed from the same disk of gas and dust that surrounded the young Sun, but their peculiarities, such as the retrograde orbit of Triton, suggest that Neptune's moon system has undergone significant changes over time. Neptune's distance from the Sun and its position at the edge of the solar system make it difficult to study in detail. The Voyager 2 spacecraft, which passed by Neptune in 1989, provided the most detailed images and data of the planet and its moons. But since then, no spacecraft have visited the distant ice giant. Yet, the study of Neptune's moons and rings continues to provide valuable insights into the dynamics of the outer solar system and the formation of planetary systems. Future missions to Neptune, such as the proposed Neptune Odyssey mission, are expected to return with even more detailed information about the planet and its moons. These missions could unlock the secrets of Neptune's composition, its atmosphere, and the potential for life on its icy moons. With each new discovery, Neptune moves from being a distant, icy world to a crucial piece of the puzzle in understanding our solar system. Neptune, with its dynamic atmosphere, intense storms, retrograde moons, and distant position in the solar system, continues to be a source of fascination and mystery for astronomers. It's a world that challenges our understanding of planetary systems, offering new insights into the workings of distant planets and the possibility of life in the outer reaches of the solar system. The Surf, Venus, the second planet from the Sun, is a world of extremes, with conditions so harsh that it challenges the limits of what we consider survivable. Often called Earth's twin due to its similar size and composition, Venus is far from the hospitable planet it may appear to be at first glance. Instead, it is a place of unrelenting heat, crushing pressure, and toxic clouds that make it one of the most inhospitable environments in the solar system. Venus's atmosphere is thick with clouds of sulfuric acid, creating a dense veil that traps heat and prevents us from seeing its surface clearly. These clouds contribute to the planet's runaway greenhouse effect, where sunlight enters the atmosphere but cannot escape, causing the planet's temperature to soar to unimaginable heights. Venus's surface temperatures average around 465 degrees Celsius, 869 degrees Fahrenheit, hot enough to melt lead. This extreme heat makes Venus the hottest planet in our solar system, even though it's not the closest planet to the Sun. The heat is caused by the thick carbon dioxide-rich atmosphere, which traps heat far more effectively than Earth's atmosphere. The pressure on Venus's surface is another insurmountable challenge. It is approximately 92 times greater than Earth's, about the pressure found 900 meters, 3,000 feet, under the ocean. If you were standing on the surface of Venus, you would feel the weight of the atmosphere pressing down on you as though you were 1,000 meters underwater. The air on Venus is so dense that it can crush spacecraft that attempt to land without the proper protection. Yet despite its extreme conditions, Venus remains a fascinating planet, offering us critical clues about climate dynamics and planetary evolution. It is often considered a cautionary tale in our search for Earth-like planets. The extreme heat and the thick clouds on Venus tell the story of how the planet's climate went awry, possibly due to a runaway greenhouse effect that caused the surface temperature to rise uncontrollably. Scientists have long debated whether Venus was once more Earth-like, with oceans and a more temperate climate, before undergoing a catastrophic change. Venus's surface is a desolate landscape, dominated by vast plains of volcanic rock and mountain ranges. While there is no definitive evidence of plate tectonics, like Earth's shifting crust, the surface of Venus is dotted with thousands of volcanoes. Some of these volcanoes, such as Mont Mons, are large enough to dwarf Mount Everest. The heat from Venus's interior is likely responsible for these volcanic features, which continue to shape the surface to this day. However, unlike Earth's volcanoes, which erupt lava, Venus's volcanoes may expel molten rock and gases like carbon dioxide and sulfur. One of the most striking features on Venus's surface is its vast, sprawling lava plains, which stretch for thousands of kilometers. These plains are thought to be relatively young, geologically speaking, suggesting that Venus may still have active volcanic processes beneath its surface. The presence of these volcanic regions raises the possibility that Venus might not be as geologically dormant as we once thought. Despite the overwhelming conditions, Venus has been the subject of numerous missions that have tried to reveal the secrets of its surface. The Soviet Union's Venera program, which operated in the 1960s and 1970s, sent several spacecraft to Venus, with Venera 7 being the first to send back data from the surface in 1970. These early missions endured only a short time on Venus before being destroyed by the extreme conditions, but they provided invaluable data about the planet's atmosphere and surface. Later missions, such as NASA's Magellan spacecraft, mapped Venus's surface using radar, offering the clearest view of the planet's topography to date. Venus also possesses some of the most interesting and perplexing weather patterns in the solar system. The thick atmosphere of Venus is made up primarily of carbon dioxide, with clouds of sulfuric acid droplets and traces of water vapor. These clouds create a highly reflective surface, making Venus one of the brightest objects in the night sky. The atmosphere is in constant motion, with winds that can reach up to 300 kilometers per hour, 186 miles per hour, in the upper clouds. These winds, along with the planet's extreme temperatures, contribute to a dynamic and ever-changing environment. The winds on Venus are also notable for their extraordinary speed, particularly in the upper atmosphere. These superrotational winds circle the planet in a matter of just a few days, far faster than the planet itself rotates. Venus takes about 243 Earth days to complete a full rotation on its axis, but its winds can complete a rotation in just 4 Earth days. This phenomenon of superrotation has baffled scientists, who are still trying to understand how Venus's atmosphere is able to sustain such fast winds despite the planet's slow rotation. Despite its inhospitable conditions, Venus holds clues to many of the fundamental questions in planetary science. How did the planet evolve from a potential Earth-like world to the extreme environment we see today? What caused the runaway greenhouse effect? Could Venus have once had liquid water, or was it always a dry, barren world? The study of Venus provides answers not only to questions about our neighboring planet, but also insights into the processes that shape all planets, including our own Earth. Venus's proximity to Earth makes it an important planet to study in the search for other potentially habitable worlds. While Venus itself is unlikely to support life, its history could help scientists understand what happens when a planet's climate goes beyond the tipping point of habitability. The study of Venus's atmosphere, surface conditions, and geological features offers valuable lessons for the future of Earth, especially as we grapple with our own changing climate. Future missions to Venus, such as NASA's Veritas, Venus Emissivity, Radio Science, INSAR, Topography and Spectroscopy, and ESA's Envision missions, are expected to provide more detailed information about the planet's surface, atmosphere, and geological activity. These missions will further our understanding of Venus's complex climate system and how it evolved over time, shedding light on the mysteries of this extreme world. Venus is a planet that constantly challenges our perceptions of what is possible in the universe. With its extreme heat, crushing pressure, and toxic atmosphere, it seems almost impossible to study in detail. Yet, The data we continue to gather from Venus missions deepens our understanding of planetary science, teaching us about the delicate balance required for a planet to sustain life, or the catastrophic consequences of that balance tipping too far. The enigma of Mars. Mars, the red planet, has captivated humanity for centuries. With its barren surface and mysterious history, could life have once existed there? Or is it an ancient desert, forgotten by time? Mars is a world of contrasts. Its rusty, reddish hue makes it one of the most striking objects in the night sky. While it seems to be a desolate, inhospitable place, it holds a deeper mystery beneath its rocky, dusty exterior. At first glance, Mars appears to be the most Earth-like planet in the solar system. It has seasons, polar ice caps, and even the possibility of water, but its environment is vastly different from ours. Mars's atmosphere is thin and composed primarily of carbon dioxide, with only trace amounts of oxygen and nitrogen. This means that any form of life that could have existed on Mars would have had to survive in an environment with far less breathable air and much colder temperatures than we experience on Earth. The surface of Mars is covered in massive volcanoes, deep valleys, and vast plains of red dust. One of the most famous features of Mars is Olympus Mons, the largest volcano in the solar system. Standing nearly 13.6 miles, 22 kilometers, high, Olympus Mons is nearly 3 times the height of Mount Everest. Its size suggests that it formed over millions of years without significant erosion, meaning that Mars was once geologically active. Mars also has one of the largest canyon systems in the solar system, Valles Marineris. This immense canyon stretches over 2,500 miles, 4,000 kilometers, and is up to 7 miles, 11 kilometers, deep in some places. Valles Marineris is so large that it could easily fit the entire Grand Canyon within its bounds. The origin of this canyon system remains a subject of debate. Some scientists believe it was caused by tectonic forces, while others suggest it could have formed through erosion by ancient water. While Mars is known for its dusty, arid landscape today, scientists believe that it was once much wetter. Evidence gathered from rovers and orbiters has shown that Mars once had rivers, lakes, and possibly even an ocean. Features such as dried-up riverbeds, mineral deposits that form in the presence of water, and signs of ancient shorelines suggest that liquid water once flowed freely on the Martian surface. One of the most exciting discoveries related to Mars's past is the presence of frozen water at its poles. Mars has 2 polar ice caps made of water ice and carbon dioxide ice. During the Martian summer, part of the carbon dioxide ice sublimes into gas, causing dust storms that can envelop the entire planet. However, the water ice remains year-round. In recent years, scientists have detected evidence of underground water reservoirs, which could be key to understanding whether life ever existed on Mars, or whether life could one day thrive there again. Mars's thin atmosphere, combined with the absence of a magnetic field, makes it impossible for the planet to retain the kind of atmosphere necessary for life as we know it. Without a magnetic field to protect it from solar radiation, the Martian atmosphere was gradually stripped away by the solar wind. As a result, the planet's once warmer and wetter conditions have given way to the frozen, barren landscape we see today. However, the possibility of life on Mars isn't entirely ruled out. While the planet's surface is inhospitable, scientists believe that microbial life could have once existed in Mars's ancient past. Evidence from meteorites that have fallen to Earth suggests that Mars might have had conditions similar to those on Earth early in its history, including liquid water. Some scientists also think that microbial life might still exist beneath the surface, where conditions are more stable and where liquid water may still exist in underground aquifers. In recent years, rovers such as NASA's Curiosity and Perseverance have been exploring Mars's surface, searching for signs of ancient life. Perseverance, for example, is specifically designed to look for ancient microbial life and to collect soil samples that could be returned to Earth in future missions. The discoveries made by these rovers have provided crucial evidence about the planet's history and its potential to support life. Mars is also the site of human exploration. Plans are already underway to send astronauts to Mars, with missions slated for the coming decades. NASA's Artemis program, which aims to return humans to the Moon, will serve as a stepping stone to the eventual goal of reaching Mars. Scientists and engineers are working tirelessly to develop the necessary technology to send humans to Mars, from spacecraft capable of surviving the long journey to habitats that can protect astronauts from the harsh conditions on the Martian surface. Despite the challenges, the prospect of human life on Mars is one of the most exciting frontiers in space exploration. With its similarities to Earth, Mars remains the most likely candidate for colonization or habitation in the distant future. The first step toward this goal is understanding the planet better, and the ongoing robotic missions are laying the groundwork for future human exploration. One of the biggest mysteries surrounding Mars is whether it had an atmosphere capable of sustaining life long enough for complex organisms to evolve. The evidence suggests that Mars may have had a much thicker atmosphere in the past, with a stronger greenhouse effect that kept the planet warmer and wetter. However, over time, this atmosphere was lost, and the planet became cold and dry. Understanding how this process occurred could provide valuable insight into the history of Earth and how planets evolve over time. While Mars's surface remains a harsh and inhospitable environment, the planet holds secrets that continue to fascinate scientists. The quest to uncover these secrets is just beginning, and each new discovery brings us closer to understanding the history of our solar system and whether life could have ever existed on Mars. As we continue to explore Mars with our rovers and, eventually, with human explorers, we edge closer to one of the greatest questions in science. Did life ever exist on Mars? Part 8. The Mystery of Dark Matter and Dark Energy. The Unknowns of the Universe. In the vast, seemingly infinite expanse of the cosmos, we know more about the stars, planets, and moons than ever before. But there are parts of the universe that remain shrouded in mystery: dark matter and dark energy. These two invisible forces make up the majority of the universe, yet we know remarkably little about them. What we do know, however, is that they play a crucial role in shaping the cosmos. Dark matter, a mysterious substance that cannot be seen or directly detected, accounts for about 27% of the universe's mass energy content. Though it is invisible, its gravitational effects are felt throughout the cosmos. Without dark matter, galaxies would fly apart, unable to hold themselves together. It's what holds galaxies, galaxy clusters, and the entire structure of the universe in place. In essence, dark matter acts as the glue that binds everything in the universe, but we don't yet understand what it's made of or how it interacts with normal matter. Dark matter doesn't emit, absorb, or reflect light, making it impossible to detect with conventional telescopes. Instead, scientists infer its presence through the way it affects the motion of galaxies and galaxy clusters. For instance, when we observe galaxies, we notice that the outer regions of these galaxies are rotating much faster than expected. According to the laws of gravity, the stars at the edges of galaxies should be flung out into space, but they aren't. The presence of dark matter accounts for this discrepancy. It exerts a gravitational pull that keeps everything in place, preventing galaxies from falling apart. Despite extensive efforts, scientists have yet to directly detect dark matter. There are various hypotheses about its composition. One possibility is that dark matter is made up of particles known as WIMPs, or weakly interacting massive particles, which would be very heavy but interact only through gravity and the weak nuclear force. Another possibility is that dark matter could be made of axions, tiny particles that are even lighter than neutrinos. Various experiments, including underground detectors and high-energy particle accelerators, are underway to try and detect these elusive particles. But so far, dark matter remains an enigma. Then there's dark energy, which is even more puzzling. Dark energy is the force that is causing the universe to expand at an accelerating rate. While dark matter acts like a cosmic glue, holding things together, dark energy is doing the opposite. It is pushing galaxies away from each other, causing the very fabric of space-time to stretch and grow. Dark energy makes up approximately 68% of the universe, and it is one of the greatest mysteries of modern science. Dark energy was first theorized in the late 1990s when two teams of astronomers, studying distant supernovae, discovered that the expansion of the universe was not slowing down, as expected, but speeding up. This unexpected discovery forced scientists to consider the possibility of a repulsive force, a force that pushes galaxies apart, counteracting the effects of gravity. Since then, the study of dark energy has become one of the central quests in cosmology. Unlike dark matter, which interacts through gravity, dark energy is believed to act uniformly across space. It doesn't clump together in certain regions, but is instead spread evenly throughout the universe. The exact nature of dark energy is still unknown. One leading theory is that it is a property of space itself, and as the universe expands, more dark energy is created. Another theory, called the cosmological constant, suggests that dark energy is a fixed amount, constantly filling the universe with a repulsive force. Understanding dark matter and dark energy is crucial to understanding the ultimate fate of the universe. These forces are driving the evolution of the cosmos, dictating the way galaxies form and evolve, and determining how the universe will change in the future. Will the universe continue to expand forever, becoming colder and emptier over time? Or will the expansion slow down and reverse, eventually collapsing back in on itself in a big crunch? The presence of dark energy suggests that the universe will continue to expand, but for how long, and what will be the end result? These questions remain unanswered. The study of dark matter and dark energy is not just about understanding the cosmos. It is also about understanding the fundamental nature of reality itself. These mysterious forces challenge our understanding of physics, space, and time. They stretch the limits of what we know about the universe, forcing scientists to rethink the laws that govern everything from the motion of planets to the very fabric of spacetime. Current and future observations may help unlock some of these secrets. The upcoming James Webb Space Telescope, with its unprecedented ability to observe the early universe in infrared wavelengths, could provide crucial insights into the nature of dark matter and dark energy. Observatories on Earth, like the Large Hadron Collider, continue to probe the fundamental particles that may make up dark matter, while space missions to distant galaxies and clusters of galaxies will provide more data about how dark energy is affecting the expansion of the universe. As we venture deeper into the cosmos, we continue to uncover more about the forces that govern everything we know. Dark matter and dark energy may remain elusive for now, but with each discovery, we inch closer to understanding these mysterious forces and the role they play in shaping the universe. The quest to understand dark matter and dark energy is far from over, and with it comes the promise of a deeper understanding of the universe and our place within it. Exploring the cosmos beyond. Could there be other universes beyond our own? A multiverse where every possibility plays out in parallel worlds. This idea may sound like science fiction, but it's a concept that has captured the imaginations of scientists and philosophers alike for decades. The search for the multiverse is one of the most fascinating and mind-bending frontiers of modern theoretical physics. The multiverse theory proposes that our universe, the one we observe with our telescopes, the one that holds galaxies, stars, and planets, could be just one of many universes, each with its own laws of physics, constants, and structures. In other words, there might be an infinite number of parallel universes, some similar to ours, others wildly different. Some may even have different types of matter or completely different dimensions of space and time. It's a theory that pushes the boundaries of what we know about reality, yet it remains deeply rooted in the principles of physics. The foundation for the multiverse theory comes from quantum mechanics and cosmology. In quantum mechanics, there's an idea called the many worlds interpretation, which suggests that every time a decision or event happens, the universe splits, creating a new, parallel universe for each possibility. This means that for every decision or random occurrence in the universe, there might be countless alternate versions of reality, each one playing out in its own separate universe. So, in a way, every moment creates an infinite number of parallel worlds. In cosmology, the multiverse theory is linked to the idea of cosmic inflation. Cosmic inflation refers to a period of rapid expansion of the universe that occurred just moments after the Big Bang. According to some versions of inflationary theory, this expansion could have happened not just once, but many times, creating multiple bubbles of spacetime, each one evolving into its own universe. These bubbles could be completely independent of one another, with different laws of physics, different constants, and even entirely different dimensions of space. One version of the multiverse theory is the string theory landscape, which suggests that the universe we live in is just one of many possible configurations of the extra dimensions predicted by string theory. String theory proposes that the fundamental building blocks of the universe are not particles, but tiny, vibrating strings. These strings can exist in multiple dimensions, beyond the familiar 3 dimensions of space and 1 of time. The landscape refers to the vast number of ways these strings can vibrate, each configuration potentially giving rise to a different universe with its own set of physical laws. Another intriguing idea comes from the concept of the brain multiverse, which arises from string theory's extended version, known as M-theory. In this scenario, our universe is one 3-dimensional brain floating in a higher dimensional space. Other parallel universes, also existing on their own brains, could be floating alongside ours in this higher dimensional space, separated by an unseen force. These other universes could be similar to ours or completely different, and we may never be able to interact with them directly. But the idea that our universe could be just one of many, all floating in a higher dimensional realm, is a tantalizing possibility. Perhaps one of the most profound implications of the multiverse theory is the potential for other universes to have completely different laws of physics. In our universe, gravity is a weak force compared to other fundamental forces like electromagnetism. But in some other universes, gravity could be much stronger or weaker, leading to very different structures and behaviors of matter. In these alternate universes, life as we know it might not even be possible, or life could arise in ways unimaginable to us. While the idea of the multiverse may seem far-fetched, there are actually several ways to test it, even if directly observing parallel universes is beyond our current capabilities. One potential way to detect the existence of other universes is through the study of the cosmic microwave background radiation, the faint afterglow of the Big Bang. Some scientists believe that if our universe has collided with another universe in the past, traces of this interaction might be detectable in the cosmic microwave background. Finding these imprints could provide the first evidence of the multiverse. Another approach comes from the study of black holes. Black holes are regions of space where gravity is so intense that not even light can escape. Some theories suggest that black holes could be portals to other universes, or they might contain information about the origins of the universe itself. If we could understand more about the nature of black holes and their event horizons, we might uncover more clues about the nature of space, time, and the possibility of other worlds. Despite these theoretical ideas, the search for the multiverse remains one of the most challenging and elusive quests in modern physics. While the evidence is largely indirect, and much of it is still speculative, the possibility that our universe is just one of many is too captivating to ignore. The multiverse challenges our understanding of reality, offering a view of the cosmos far beyond what we can directly observe, one that suggests the very fabric of existence may be far more vast and far stranger than we could ever imagine. Exploring the cosmos beyond our own universe pushes us to ask fundamental questions about the nature of existence. What is the nature of reality? What determines the laws of physics? Are we truly alone in the cosmos? Or could there be other realms of existence, parallel to ours, where different versions of life and time unfold? The multiverse theory invites us to think beyond the confines of our own universe and consider the possibility that the cosmos is far more complex, mysterious, and infinitely vast than we ever imagined. Part 9. The future of space exploration. The future of human space travel. Upcoming space missions. As we continue to look deeper into the cosmos, new space missions are on the horizon, promising to push the boundaries of human knowledge and explore the unknown regions of space. These upcoming missions are set to unlock mysteries about our solar system, distant stars, and even the possibility of life beyond Earth. From exploring new planets to uncovering the secrets of distant moons, the next few years will bring groundbreaking discoveries. NASA's Artemis program is among the most anticipated missions. This mission aims to return humans to the moon for the first time in over 50 years. The goal is not just to land astronauts on the lunar surface, but to establish a sustainable presence on the moon. Artemis will set the stage for future exploration of Mars by testing new technologies, gathering valuable data about the lunar surface, and even building the gateway, an outpost that will orbit the moon and serve as a launch point for deeper space exploration. One of the key objectives of Artemis is to send the first woman and the next man to the moon's surface. They will explore areas near the lunar South Pole, where water ice has been detected, which could one day be used to support long-term human habitation. This water could also serve as a vital resource for generating oxygen and fuel for future missions to Mars. Following the success of Artemis, the next major human endeavor will be Mars exploration. NASA's Perseverance rover, which is currently on Mars, has already begun the task of searching for signs of ancient life and collecting samples for future return missions. The next step is the launch of a mission to bring these samples back to Earth. This will be the first time we'll retrieve Martian soil, and it could provide the answers we've been seeking about whether life ever existed on Mars and what the planet was like billions of years ago. In addition to NASA's efforts, other countries and private companies are contributing to the push for Mars exploration. SpaceX, led by Elon Musk, is actively developing the Starship, a fully reusable spacecraft that could carry humans to Mars. SpaceX aims to make life multiplanetary by establishing a colony on Mars. Their goal is ambitious, aiming for the first crewed missions to Mars in the mid-2020s, with a longer-term vision of sending thousands of people to the Red Planet. Beyond Mars, one of the most exciting upcoming missions is NASA's James Webb Space Telescope, set to launch in December 2021. Webb will be the most powerful space telescope ever built, designed to see further back in time than ever before. It will provide a clearer view of the early universe, helping us understand how galaxies, stars, and planets formed. Webb will also be capable of investigating the atmospheres of exoplanets to determine if they could support life. Its infrared capabilities will allow us to peer through cosmic dust clouds to study star-forming regions, black holes, and the oldest galaxies. NASA isn't the only space agency making advancements in space exploration. The European Space Agency, ESA, is set to launch the Jupiter Icy Moons Explorer (JUICE) mission in 2022. This spacecraft will study Jupiter's moons Ganymede, Callisto, and Europa. These moons are believed to harbor subsurface oceans beneath their icy crusts, and JUICE will investigate whether these moons could support life. Europa, in particular, has been a prime target for scientists, as its subsurface ocean could potentially harbor microbial life. China is also making significant strides in space exploration. The Tianwen-1 mission, launched in 2020, successfully landed the Zhurong rover on Mars, making China the third country to land a rover on the Red Planet. Tianwen-1 will continue to explore the Martian surface, searching for evidence of water and potential signs of life. Looking forward, China plans to establish its own space station, Tiangong, and is aiming to send astronauts to the moon in the coming decades, contributing to the global space exploration effort. Another exciting mission is the return of samples from the asteroid Bennu. NASA's OSIRIS-RX spacecraft successfully collected samples from Bennu, a near-Earth asteroid that scientists believe holds clues to the early solar system and the origins of water and organic molecules on Earth. The spacecraft will return the samples to Earth in 2023, and these precious materials will be analyzed for the first time in laboratories on Earth. Beyond our own solar system, missions like the James Webb Space Telescope will help us investigate the potential for life on exoplanets, planets that orbit stars outside our solar system. In the coming decades, we will continue to discover and characterize exoplanets, particularly those in the habitable zone where liquid water could exist. The search for Earth-like worlds is one of the most exciting areas of modern astronomy, and future missions will aim to study the atmospheres of these planets in more detail, looking for signs of habitability or even life. One of the most anticipated space missions of the future is the exploration of the outer solar system. NASA's planned Dragonfly mission to Titan, Saturn's largest moon, will launch in the mid-2020s. Dragonfly will land on Titan and explore its surface, studying the moon's organic chemistry and its potential for supporting life. Titan's thick atmosphere and methane lakes make it one of the most intriguing places to search for life, even if it's radically different from life as we know it. As we continue to push the boundaries of space exploration, these upcoming missions will play a crucial role in expanding our understanding of the universe. From the search for life on Mars and beyond, to understanding the early universe with the James Webb Space Telescope, the future of space exploration is full of incredible possibilities. These missions will shape our future, not only by answering fundamental questions about the cosmos, but also by opening new frontiers for humanity to explore and, one day, inhabit. The next steps in space exploration are not just about reaching new destinations. They are about answering questions that have captivated us for millennia. Are we alone in the universe? What happened in the earliest moments after the Big Bang? How did life begin on Earth, and can it exist elsewhere? These upcoming missions bring us closer to understanding our place in the cosmos and the possibility of life beyond our planet.
Mars colonisation.
Mars has long captivated the human imagination. For centuries, we've looked to the red planet, wondering if it might one day become our second home. With its proximity to Earth and its Earth-like qualities, Mars is the most viable candidate for colonization in our solar system. But transforming Mars into a livable environment for humans will require overcoming numerous challenges. Currently, Mars is a hostile, barren world. It has a thin atmosphere, composed mostly of carbon dioxide, with barely any oxygen. Temperatures can drop to -195 degrees Fahrenheit, -125 degrees Celsius at the poles during winter, and the surface is bombarded by harmful radiation from the sun. The planet's gravity is only about 38% of Earth's, which means that any human colonists would face new challenges related to health and long-term living conditions. In short, living on Mars is not just about setting foot on the planet. It's about adapting the entire environment to support human life. One of the biggest challenges to Mars colonization is creating an atmosphere capable of sustaining human life. Mars' thin atmosphere provides no protection from the sun's harmful rays, and without a protective shield, colonists would be exposed to dangerous levels of radiation. One proposed solution is terraforming, altering the Martian atmosphere to make it more Earth-like. This could involve releasing greenhouse gases into the atmosphere to warm the planet, a process that could take centuries or even millennia. However, the possibility of terraforming remains highly debated, as the necessary technology and resources might be beyond our current capabilities. Until Mars' atmosphere can be made habitable, human colonists will need to live in enclosed habitats. These habitats will have to provide a controlled environment where oxygen is produced, temperatures are regulated, and radiation is blocked. Some proposals suggest building habitats beneath the surface, where Mars' thick regolith could offer protection from radiation and extreme temperatures. Others envision the use of inflatable domes or underground bunkers as temporary solutions. Regardless of the method, the colonization of Mars will require innovation, research, and experimentation. Water is another critical resource for Mars colonization. While we've discovered that Mars has water ice at its poles and possibly liquid water beneath its surface, accessing this water is a significant challenge. The process of extracting water from the Martian ice will require specialized equipment, and the technology to safely melt and purify this water is still in its infancy. Until Mars' water supply can be fully utilized, colonies will need to rely on recycled water, creating a closed-loop system similar to the ones used by astronauts on the International Space Station. The quest to send humans to Mars is already underway, and private companies like SpaceX are leading the charge. Elon Musk's ambitious plan to establish a colony on Mars involves developing the Starship spacecraft, designed to carry humans and cargo to the Red Planet. Musk envisions a fleet of starships making regular trips to Mars, carrying the necessary supplies, equipment, and eventually colonists. The long-term goal is to create a self-sustaining city on Mars that could grow into a thriving colony, with the ability to support thousands of people. NASA also has plans to send humans to Mars, with missions expected to take place in the 2030s. NASA's Artemis program, which aims to return humans to the Moon, will serve as a stepping stone to Mars exploration. The Moon's surface is a useful testing ground for the technologies that will be required for Mars missions, including habitats, life support systems, and radiation protection. By establishing a permanent presence on the Moon, NASA will gather valuable data that can be applied to future Mars missions. Beyond the technological and logistical challenges, the psychological effects of living on Mars are a critical consideration for colonization. With Mars' vast distance from Earth, about 140 million miles at its closest, colonists will face extreme isolation. Communication with Earth will take anywhere from 20 to 40 minutes one way, making real-time conversation impossible. The psychological stress of long-term isolation, limited social interaction, and the monotony of life on Mars will require new strategies for mental health and well-being. Experts are already studying how to address these issues, including developing support systems, virtual reality environments, and even artificial intelligence companions to help manage the emotional challenges of colonization. Long-term colonization will also require creating a sustainable economy on Mars. Establishing industries such as mining, agriculture, and manufacturing will be essential to maintaining a colony. Mars has valuable resources, such as water ice, minerals, and metals, that could be mined and used for construction, energy production, and other needs. Growing food on Mars will require the development of hydroponics or other soil-free farming techniques, allowing colonists to produce their own food. These industries will need to be self-sufficient, as transporting resources from Earth will be prohibitively expensive and inefficient in the long run. While sending humans to Mars is an incredible achievement, it's only the beginning of humanity's journey in space. Establishing a permanent presence on Mars will require collaboration, innovation, and the resilience of humanity as a whole. The potential benefits of Mars colonization are immense. Not only could it serve as a backup for humanity in case of disaster on Earth, but it could also be the first step toward further exploration of the solar system, including the moons of Jupiter and Saturn and beyond. As we look toward the future, the dream of colonizing Mars becomes more and more possible. While many challenges remain, each step taken toward Mars exploration brings us closer to making this dream a reality. It's not just about reaching Mars. It's about creating a new home for humanity, a place where we can thrive, explore, and expand our presence beyond Earth. The future of Mars colonization is still unfolding, and the journey is only just beginning. The future of humanity in space. As we look to the stars, the future of humanity in space is no longer just a dream. It is becoming a tangible goal. The idea of humans living and thriving beyond Earth has captured our collective imagination for centuries. Today, we stand on the cusp of a new era in space exploration, one that will redefine the boundaries of human existence and open up new frontiers across the cosmos. One of the most ambitious goals for humanity is to establish a permanent presence beyond our home planet. This could begin with the Moon, but it is Mars that is capturing the most attention. A growing number of space agencies and private companies are actively working towards sending humans to the Red Planet. The potential for Mars to become a second home for humanity is exciting, but it is also fraught with challenges. The environment on Mars is harsh and unforgiving. Temperatures drop well below freezing, the atmosphere is too thin to provide breathable air, and the planet's surface is constantly bombarded by cosmic radiation. Overcoming these obstacles will require cutting-edge technology, innovative problem-solving, and a deep commitment to exploration. But the journey to Mars is just the beginning. The longer-term vision for humanity in space is one of expansion. Beyond Mars, there are moons of Jupiter and Saturn that are thought to hold the potential for life, such as Europa, Enceladus, and Titan. These moons have subsurface oceans that could harbor microbial life, or at least contain the building blocks necessary for life. These intriguing worlds could become the next destinations in humanity's quest to understand the cosmos. To achieve this grand vision, humanity will need to develop the technology to live and work in space for extended periods. Space habitats, capable of supporting human life, will need to be built to withstand the harsh conditions of space. These habitats must not only provide protection from radiation and extreme temperatures, but they must also be self-sustained. Systems for growing food, recycling water, and producing oxygen will be essential for long-term survival in space. Moreover, the development of new propulsion technologies is crucial. Traditional rocket technology, while effective for short missions, may not be efficient enough for longer journeys. Concepts like nuclear propulsion, which could dramatically reduce travel times to distant destinations, are being explored by scientists. By reducing travel time, these technologies could make it possible for humans to travel to other star systems, opening up entirely new possibilities for exploration and settlement. Space mining is also a crucial component of humanity's future in space. The moon and asteroids contain vast resources, including precious metals and minerals, that could be vital for building infrastructure on other worlds. Mining these resources could provide the materials needed for constructing habitats, spacecraft, and other essential technologies. By tapping into space's vast resources, humanity could reduce its dependence on Earth and begin building a truly off-planet civilization. One of the most exciting developments in the future of space exploration is the prospect of space tourism. While this may seem like a distant dream, it's rapidly becoming a reality. Companies like SpaceX, Blue Origin, and Virgin Galactic are all working to make space travel more accessible to private citizens. In the coming decades, it's likely that space tourism will become more affordable, offering more people the opportunity to experience the wonders of space. This could mark the beginning of an entirely new industry, with commercial space travel becoming as common as flying across the globe. As space exploration advances, we will also face profound questions about the ethics and governance of space. Who owns space? Who has the right to mine asteroids or establish colonies on distant planets? These are issues that will need to be addressed as humanity expands beyond Earth. There will be new laws and treaties to develop, as well as international cooperation to ensure that space remains a shared resource for all of humanity. As we venture into the cosmos, we must learn to respect and protect the space around us, ensuring that our presence doesn't harm the very environments we seek to explore. Ultimately, the future of humanity in space is about more than just survival. It's about exploration, discovery, and the human spirit's endless curiosity. Space offers us the opportunity to answer some of the most profound questions we have about our place in the universe. Are we alone? How did life begin? What are the limits of human potential? These questions drive our exploration and will continue to fuel our endeavors as we push the boundaries of human achievement. The future is bright, but it is also uncertain. Humanity's journey into space is still in its infancy, and there are many challenges that must be overcome. But with each mission, each discovery, we are one step closer to creating a future in which humanity is no longer confined to Earth. The cosmos, with all its mysteries, awaits us. Space is the final frontier, not just for astronauts and scientists, but for all of humanity. The possibilities are endless, and the time is now. We are on the brink of an extraordinary new chapter in human history, one that will not only change the way we explore, but also how we live and think about our place in the universe. Closing reflections. As we drift off to sleep, we realize that the universe has so much more to offer. The answers to the deepest questions are out there, waiting to be discovered, as we continue our journey through the stars. Every moment in this vast expanse, from the birth of stars to the mystery of dark matter, brings us closer to understanding the true nature of the cosmos. Perhaps the most profound realization is that space is not just a backdrop to our lives. It is a fundamental part of our existence. Everything around us, from the air we breathe to the ground beneath our feet, is connected to the universe in ways we are just beginning to understand. The atoms in our bodies were forged in the hearts of stars long before our planet ever existed, and through that connection, we are all part of something much greater than ourselves. The universe is filled with wonders yet to be explored, and as humanity continues its quest for knowledge, we too evolve. Each mission, each discovery, brings us closer to understanding not only the cosmos but our place within it. The stars that we gaze upon tonight have watched over us for billions of years, and they will continue to do so long after we're gone, a silent testament to the eternal dance of creation and destruction. However, no matter how far we travel or how much we learn, the mysteries of space will always remain. They are a reflection of the vastness of the unknown, a reminder that no matter how much we discover, there will always be more to seek, more to understand, and more to uncover. The universe does not reveal its secrets easily, but that is part of its beauty. The infinite questions are as captivating as the answers themselves. Even as we rest, the cosmos keeps unfolding its stories of distant galaxies, dying stars, and planets that could harbor life. We may not always be awake to witness these revelations, but they are always happening, and one day we may be lucky enough to unlock them. Our journey through space is just beginning, and the possibilities ahead of us are as vast as the universe itself. Final thought. In the quiet of space, we are all stardust, drifting in the vastness, connected to each other and to everything that came before. The same particles that make up our bodies once danced through the hearts of distant stars. We are part of the ongoing story of the universe, a story that will continue long after we are gone. As the stars burn bright and the galaxies swirl in an endless dance, we are not separate from the universe, we are one with it. As we close our eyes, we can rest in the knowledge that we are all part of this grand cosmic journey, connected by the fabric of space and time. In the silence of the universe, we find peace, knowing that we are part of something much greater than ourselves. And as we drift into sleep, we can take comfort in the fact that the stars continue to shine, guiding us through the night.